Welcome, weary traveller, to a journey through the annals of scientific history. As you settle in for a night's rest, let us embark on a voyage to explore the greatest discoveries that shaped our understanding of the universe. Along the way, we'll meet some of history's most brilliant minds, men and women whose insatiable curiosity and tireless pursuit of knowledge illuminated the cosmos. Before we begin, I invite you to pause for a moment and share in the comments where in the world you're listening from and what time of day it is for you right now. It's a delight to have you here, and I'm always fascinated to learn about the diverse global audience that finds respite in these quiet histories. If you enjoy this style of calm, meandering storytelling, I encourage you to subscribe so you never miss an episode. Now make yourself comfortable, dear listener. Dim the lights if you wish, fluff your pillow, and let your mind drift as we set sail to the dawn of modern science. Our story begins not with a thunderous bang, but a whisper, a quiet revolution in thought that would soon reverberate through the ages. The scene is Europe, circa 1500 AD. The Renaissance is in full bloom, and with it, a new breed of thinkers who dare to question the dogma of the past. For centuries, the prevailing wisdom held that the Earth was the centre of the universe, with the sun, moon and stars all revolving around it in perfect celestial spheres. This geocentric model, proposed by the ancient Greek astronomer Ptolemy, and refined by generations of Islamic scholars, fit neatly with both the observable motions of the heavens and the Catholic Church's teachings of an earth-centered creation. But a growing number of curious minds sensed that something didn't quite add up. The trajectories of the planets, with their odd loops and reversals, were fiendishly difficult to reconcile with a universe centred on the Earth. It was into this milieu that a quiet canon from Poland named Nicolaus Copernicus began to sow the seeds of a revolutionary idea. Copernicus was a true Renaissance man, a physician, classic scholar, translator, governor, diplomat and economist. But his passion was for the stars. In the evenings, after attending to his many official duties, Copernicus would ascend to the rooftop observatory of his cathedral and spend long hours gazing at the night sky, meticulously charting the motions of the celestial bodies. Over time, a radical notion took hold in his mind, a suspicion that perhaps the sun, not the Earth, lay at the centre of the cosmos. It was an idea that had been proposed in ancient times by Aristarchus of Samos, but had long fallen out of favour. Copernicus began to sketch out an alternative model of the universe with the sun at its heart, and the Earth and planets revolving around it in circular orbits. He worked out his theory in secret over many decades, sharing it only with a few trusted confidants. Copernicus knew his ideas would be seen as heretical by the Church, and he feared the backlash that would ensue if he published them openly. It wasn't until he lay on his deathbed in 1543 that he finally agreed to release his magnum opus, De Revolutionibus Orbium Coelestium, or On the Revolutions of the Celestial Spheres. Legend has it that Copernicus awoke from a stroke-induced coma just long enough for a friend to place an advance copy of the book in his hands. He touched it, then breathed his last, never knowing the furor his ideas would unleash on the world. At first, the Church largely ignored Copernicus' heretical notions, dismissing them as a mathematician's abstract musings, not to be taken seriously as a description of reality. The heliocentric theory might be useful for calculating planetary positions, but heaven forbid one actually believe the Earth moved. Such a notion flew in the face of both common sense and scripture. But the spark of heliocentrism had been kindled, and it soon found a new champion in the brilliant Italian astronomer and physicist Galileo Galilei. Born in 1564, 21 years after Copernicus's death, Galileo would become the first to provide observational evidence that lent credence to the sun-centered model of the universe. The key to Galileo's discoveries was a marvelous new invention, the telescope. Although Galileo did not invent the device himself, he was the first to turn it skyward and peer at the cosmos with magnified vision. In 1609, after learning about early Dutch versions of the instrument, Galileo set about building ever more powerful telescopes of his own design. Through his lenses, Galileo beheld wonders that no human eye had ever before seen. He marvelled at the cratered face of the moon, the hundreds of new stars in the Milky Way, and satellites circling Jupiter, all revelations that challenged the notion of an immutable celestial realm. But perhaps his most incendiary observations concerned the planet Venus. As Venus moved around the Sun, Galileo observed it cycling through a full set of phases just like the Moon. This was a phenomenon that simply couldn't be explained by an Earth-centered universe, but made perfect sense if Venus was orbiting the Sun. Armed with his telescopic discoveries, Galileo became a forceful advocate for the Copernican system, daring to take the heliocentric theory from abstract speculation to physical reality. In a series of writings, debates, and public lectures, he openly espoused the view of a sun-centered cosmos, despite stern warnings from church authorities. It all came to a head in 1633, when Galileo was called before the Roman Inquisition on charges of suspected heresy. After a lengthy trial, the aging astronomer was forced to kneel and publicly recant his belief in the false doctrine of heliocentrism under threat of torture and execution. According to popular legend, as Galileo rose from his knees, he muttered defiantly under his breath, "And yet it moves," referring to the Earth's motion around the Sun. While this dramatic phrase was almost certainly a later invention, it captures the spirit of Galileo's unshakable conviction in the face of institutional opposition. Broken in body but not in mind, Galileo lived out his remaining years under house arrest at his villa in Arcetri. Even in isolation, he continued his groundbreaking work in physics, exploring the laws of motion through ingenious experiments with inclined planes and pendulums. Though the Church had silenced Galileo, the scientific revolution he helped spark was already spreading like wildfire across Europe. As the 17th century dawned, the old Aristotelian conception of the universe lay in tatters, shattered by the observations of Copernicus and Galileo. But as revolutionary as their ideas were, they still rested more on geometrical arguments than physical principles. To forge the raw materials of astronomy into a truly coherent scientific framework would require the singular genius of Isaac Newton. Newton's story is one of those fateful tales in the history of science. Born on Christmas Day in 1643, the very year of Galileo's death, he seemed almost destined to carry the great astronomer's legacy to heights Galileo himself could scarcely have imagined. Growing up in the English countryside, the young Newton displayed an early fascination with all things mechanical. He built sundials, model windmills, and even a miniature working mill that actually ground grain. But his true calling lay in the realm of the mind, in the precise language of mathematics and the hidden laws that governed the universe. In 1665, as a young student at Cambridge, Newton was forced to retreat to his family estate at Woolsthorpe to escape the Great Plague that was ravaging London. It was during this period of isolation, surrounded by the tranquil orchards and bubbling brook of his childhood home, that Newton embarked on a sustained frenzy of intellectual discovery unmatched in scientific history. In the space of just 18 months, the 23-year-old Newton laid the foundations for his theories of optics and calculus, and, most significantly, began to piece together his unified theory of gravity. According to one beloved tale, the first glimmer of universal gravitation struck Newton as he observed an apple tumbling from a tree in his garden. While this story is likely embellished, it encapsulates the profound simplicity of Newton's insight, that the same force that caused an apple to fall to Earth also kept the Moon revolving in its orbit and the planets circling the Sun. Over the next 2 decades, Newton worked out the full mathematical implications of his theory of gravity, culminating in his 1687 masterpiece, the Principia Mathematica. In this monumental work, Newton not only explained the elliptical orbits of planets, but united the heavens and earth under a single set of physical laws. With one fell swoop, he banished the old Aristotelian notion of the celestial realm as a rarefied domain separate from our sublunary sphere. Newton's universal law of gravitation was as profound as it was far-reaching. Suddenly, the universe was laid bare as an immense clockwork mechanism, a cosmos whose every motion, from the orbit of a comet to the arc of a cannonball, could be described with precision by elegant mathematical equations. It was a powerful toolkit that would launch science to extraordinary heights in the centuries to come. But even Newton himself stood humbled before the vast ocean of truth that remained undiscovered. In one of his most famous reflections he mused, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. With the groundbreaking work of Copernicus, Galileo and Newton as its launching pad, the science of the heavens surged ahead in the 18th and 19th centuries. Astronomers like William Herschel and Friedrich Bessel refined the art of celestial observation to new levels of precision, cataloguing thousands of stars and nebulae, and even inferring the existence of unseen companions from tiny wobbles in stellar motions. Meanwhile, brilliant mathematical physicists like Joseph-Louis Lagrange and Pierre-Simon Laplace extended Newton's methods to ever more elaborate calculations, explaining the subtleties of lunar orbits and predicting the existence of new planets from slight discrepancies in the motions of those already known. By the dawn of the 20th century, the majestic framework of classical physics seemed complete, a cathedral of immutable laws that governed everything under and beyond the sun. Little did scientists suspect that the greatest upheavals were yet to come, that a new generation of scientific revolutionaries was about to shatter the Newtonian universe and rebuild it anew. But that is a story for another night, dear listener. For now, let us pause and marvel at the audacity of those first intrepid explorers, Copernicus, Galileo, Newton, and all the other restless souls who dared to dream of a cosmos grander than the tidy Aristotelian spheres. As you drift off to sleep, picture yourself among these great minds, gazing up at the wheeling firmament with fresh eyes. What hidden marvels might you glimpse? What eternal truths could you unravel? The universe is vast and the night is long. Let your imagination roam free. And so we conclude this first chapter in our survey of the greatest scientific discoveries of all time. In our next episode, we'll venture into the invisible realm of electricity and magnetism, where a new band of scientific luminaries will shed light on the most elusive of nature's forces. Until then, I bid you a peaceful rest. May your dreams be filled with the music of the spheres and the beauty of eternal truths waiting to be discovered. This is your humble narrator, signing off. Indeed, Einstein's explanation of the photoelectric effect was a pivotal moment, shaking the very foundations of physics. But even as scientists grappled with these revolutionary ideas in the early 20th century, the cosmos had more surprises in store. As we gaze up at the night sky, it's natural to wonder about our place in the grand scheme of things. How large is the universe? Has it always been this way? These questions would soon be illuminated by the tireless work of an American astronomer named Edwin Hubble. In the 1920s, Hubble was using the colossal 100-inch Hooker telescope at Mount Wilson Observatory in California to observe distant nebulae, fuzzy patches of light scattered across the sky. Many astronomers believed these were clouds of gas and dust within our own Milky Way galaxy. But Hubble's keen observations would soon shatter that assumption. Peering through the eyepiece night after night, Hubble meticulously studied individual stars within the nebulae, and then came the revelation. Some of these stars were astonishingly bright, far brighter than any star in the Milky Way. The only way they could appear so dim from Earth was if they were incredibly far away, millions of light years beyond our galaxy. With mounting evidence, Hubble boldly announced his finding in 1924. The universe extended far beyond the Milky Way. Those nebulae were in fact distant island universes or galaxies, each containing billions of stars. The Milky Way was just one of countless galaxies adrift in a vast cosmic ocean. Hubble's discovery sent shockwaves through the astronomical community. Suddenly, the universe had grown immensely in size, but that was only the beginning. In 1929, Hubble began studying the spectra of light from dozens of galaxies. Working with Milton Humason, he noticed something peculiar. The spectral lines were shifted toward the red end of the spectrum. This redshift indicated the galaxies were moving away from us, like a cosmic version of the Doppler effect. Even more intriguing, the farther away a galaxy was, the faster it appeared to be receding. This was no mere coincidence. Hubble had stumbled upon one of the greatest discoveries in the history of science, the expansion of the universe. According to his data, space itself was stretching, carrying galaxies along with it. It was a staggering realization, one that would forever change our conception of the cosmos. As news of Hubble's findings spread, theoretical physicists set to work trying to explain this cosmic expansion. One of them was a Belgian priest and astronomer named Georges Lemaitre. Unbeknownst to Hubble, Lemaitre had already been exploring similar ideas. In 1927, 2 years before Hubble's landmark paper, Lemaitre had proposed that the universe began in a hot, dense state, and had been expanding ever since. He even derived an equation relating a galaxy's distance to its speed of recession, beating Hubble to the punch. But Lemaitre took the idea a step further. If the universe was expanding, he reasoned, then running the clock backwards would imply the universe had a beginning, a day without a yesterday, as he poetically put it. Lemaitre envisioned a primeval atom from which the entire cosmos burst forth in a tremendous explosion, an idea he called the hypothesis of the primeval atom, a theory we know today as the Big Bang. While some scientists were initially skeptical of the Big Bang, the evidence would soon become overwhelming. In 1948, physicists Ralph Alpher and George Gamow were studying the theory and made a stunning prediction. If the universe began in a hot, dense state as the Big Bang proposed, there should be a faint afterglow of radiation permeating all of space, a relic of the universe's fiery birth. This afterglow came to be known as the cosmic microwave background. Alpha and Gamow calculated that the expansion of the universe would have cooled this primordial fireball to a frigid few degrees above absolute zero. But detecting it would prove to be a challenge. It would take a pair of unsuspecting radio astronomers to make one of the greatest accidental discoveries in the history of science. In 1964, Arno Penzias and Robert Wilson were working with the Holmdel-Horn antenna in New Jersey, a device built to detect radio waves bounced off echo balloon satellites. But they kept picking up a persistent, annoying hiss in their data, a noise they couldn't seem to get rid of. They checked the antenna for defects, ruled out interference from nearby New York City, and even scraped out pigeons nesting in the horn, thinking their droppings might be causing the hiss, but nothing worked. The noise was coming from everywhere at once, even from the empty sky. Perplexed, Penzias and Wilson soon learned of Alpha and Gamow's prediction of the cosmic microwave background. Realizing the significance of their discovery, they published their findings in 1965. The hiss they had detected was the first observational evidence for the Big Bang, the lingering whisper of the universe's violent birth 13.8 billion years ago. It was a Nobel-worthy achievement, one that turned the Big Bang from a speculative theory into the cornerstone of modern cosmology. Armed with the knowledge of the Big Bang and the expanding universe, scientists now had a framework to investigate the cosmos on the grandest scales. And what better way to explore the universe than to venture out into it? As the 20th century progressed, the dream of spaceflight was becoming a reality. The space race between the United States and the Soviet Union was heating up, each superpower vying to outdo the other in the conquest of the final frontier. In 1961, Soviet cosmonaut Yuri Gagarin became the first human to orbit the Earth, a triumph that shocked the American space program. Not to be outdone, President John F. Kennedy issued a bold challenge to the nation to land a man on the moon and return him safely to Earth before the end of the decade. It was an audacious goal, one that would push the boundaries of human ingenuity and technological prowess. The 1960s saw a series of milestones in the race to the moon. From the pioneering flights of the Mercury program to the daring spacewalks of Gemini, NASA was laying the groundwork for the ultimate mission. And then, on July 16, 1969, the mighty Saturn V rocket ignited its engines and roared into the sky, carrying the crew of Apollo 11 into history. 4 days later, on July 20th, Neil Armstrong and Buzz Aldrin descended to the lunar surface in the spindly Eagle lander. As an estimated 600 million people watched on television, Armstrong stepped off the ladder and uttered those immortal words, "That's one small step for man, one giant leap for mankind." For the first time, human beings had set foot on another world, fulfilling an age-old dream and opening up a universe of possibilities. The Apollo missions were a triumph of human determination and a testament to the power of science to expand the frontiers of exploration. But even as astronauts were leaving their footprints on the lunar regolith, scientists were planning an even more ambitious voyage, one that would take them to the very edge of the solar system and beyond. In 1977, NASA launched the twin Voyager 1 and Voyager 2 spacecraft on an epic journey of discovery. Their primary mission was to conduct a grand tour of the outer solar system, flying by Jupiter, Saturn, Uranus, and Neptune. But the visionary scientists behind the mission had an even grander goal in mind. They knew that after completing their planetary flybys, the Voyagers would have enough velocity to escape the Sun's gravity and venture into interstellar space, becoming the first human-made objects to do so. The Voyagers were equipped with a suite of scientific instruments to study the planets and their moons in unprecedented detail. They sent back stunning images of Jupiter's swirling clouds and volcanic moons, Saturn's shimmering rings and haze-shrouded moon Titan, and the strange and distinctive ice giants of the outer solar system. But they also carried a message from Earth, a golden record containing sounds and images selected to portray the diversity of life and culture on our planet, just in case the spacecraft were ever found by intelligent beings. As the Voyagers completed their planetary flybys in 1989, they kept on going, venturing into the unknown. In 2012, Voyager 1 made history by crossing the heliopause, the boundary where the solar wind gives way to the interstellar medium. It had left the Sun's protective bubble and entered the space between the stars. Voyager 2 would follow suit in 2018, providing invaluable data about the conditions at the edge of the solar system. Today, more than 4 decades after their launch, the Voyager spacecraft are still going strong, sending back data from over 14 billion miles away. They are a testament to the ingenuity and vision of the scientists and engineers who designed them, and to the enduring human desire to explore and understand the cosmos. Long after their power runs out, the Voyagers will keep on sailing through the void, cosmic ambassadors carrying a message of peace and hope from the pale blue dot we call home. As the 20th century drew to a close, scientists were making great strides in unravelling the mysteries of the subatomic world. The Standard Model of particle physics, developed in the 1960s and 1970s, had proven to be a remarkably successful framework for describing the fundamental particles and forces of nature. But there was one key piece of the puzzle still missing: the Higgs boson. The Higgs boson was first proposed in 1964 by British physicist Peter Higgs and independently by several other theorists. According to the theory, the Higgs boson was the manifestation of an invisible field permeating all of space, known as the Higgs field. As particles move through the Higgs field, they interact with it and acquire mass, like a celebrity trying to wade through a crowd of adoring fans. The more strongly a particle interacts with the field, the more massive it becomes. The Higgs boson was the last undiscovered particle predicted by the Standard Model, and finding it became a top priority for particle physicists around the world. But detecting the elusive boson would be no easy feat. According to the theory, the Higgs was incredibly massive and short-lived, decaying into other particles almost instantly after being created. It would take a particle accelerator of unprecedented power and precision to produce and detect the Higgs. Enter the Large Hadron Collider, or LHC, the world's largest and most powerful particle accelerator. Built by the European Organisation for Nuclear Research, CERN, near Geneva, Switzerland, the LHC is a 27-kilometre ring of superconducting magnets that accelerates beams of protons to nearly the speed of light and collides them at energies up to 13 trillion electron volts. It's a feat of engineering that pushes the boundaries of what's technologically possible. In 2012, after years of construction and testing, the LHC was finally ready to hunt for the Higgs. On July 4th of that year, physicists from 2 experiments, ATLAS and CMS, announced that they had independently observed a new particle with a mass of around 125 billion electron volts, consistent with the predicted mass of the Higgs boson. It was a historic discovery, one that sent ripples of excitement through the scientific community and beyond. The discovery of the Higgs boson was a triumph of human ingenuity and perseverance. It was the culmination of decades of theoretical work and experimental effort, involving thousands of scientists and engineers from around the world. It confirmed a key prediction of the Standard Model and cemented our understanding of how particles acquire mass. And it opened up new avenues for exploration, from studying the properties of the Higgs itself to searching for new particles and forces beyond the Standard Model. But even as particle physicists were celebrating the discovery of the Higgs, another long-predicted phenomenon was about to make waves in the scientific world. In 1916, Albert Einstein had predicted the existence of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. According to Einstein's theory of general relativity, these ripples should propagate through the universe at the speed of light, carrying information about the cataclysmic events that produced them. For decades, scientists had been trying to detect gravitational waves using increasingly sensitive instruments. But the waves were incredibly faint, and detecting them would require a level of precision that seemed almost impossible to achieve. It would take a pair of sophisticated laser interferometers, each with arms 4 kilometers long, to finally catch a glimpse of these elusive ripples. On September 14th, 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting the first direct evidence of gravitational waves. The signal, which lasted just a fraction of a second, was produced by the merger of two black holes 1.3 billion light-years away. As the black holes spiraled inward and collided, they released a burst of energy equivalent to 3 times the mass of the Sun, sending shockwaves through the cosmic fabric that rippled across the universe. The detection of gravitational waves was a stunning confirmation of Einstein's century-old prediction, and a testament to the ingenuity and perseverance of the scientists behind LIGO. It opened up a whole new way of observing the universe, allowing us to hear the cosmos in a way we never could before. Since that first detection, LIGO and its international partners have observed dozens more gravitational wave events, from the mergers of black holes to the collision of neutron stars. Each detection gives us new insight into the extreme environments where gravity reigns supreme. As we venture into the 21st century, the frontiers of science continue to expand in new and exciting directions. One of the most promising areas of research is the study of exoplanets, or planets, orbiting other stars. The first confirmed exoplanet was discovered in 1992, orbiting a pulsar about 2,300 light-years from Earth. But it wasn't until the launch of NASA's Kepler Space Telescope in 2009 that the floodgates truly opened. Kepler used the transit method to detect exoplanets, watching for the tiny dip in a star's brightness that occurs when a planet passes in front of it. Over the course of its 9-year mission, Kepler discovered over 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. It revealed a staggering diversity of worlds, from scorching hot Jupiters orbiting close to their stars to rocky super-Earths in the habitable zones where liquid water could exist. Today, the study of exoplanets is one of the most rapidly growing fields in astronomy. With new telescopes and techniques coming online, we're discovering new worlds at an unprecedented pace. And we're not just finding them, we're starting to characterize them, studying their atmospheres and compositions for signs of habitability and even life. But even as we peer outward to distant stars and galaxies, there are still mysteries to be unraveled closer to home. One of the greatest unsolved problems in modern physics is the nature of dark matter and dark energy, the invisible stuff that makes up over 95% of the universe. We know dark matter exists because of its gravitational influence on galaxies and clusters, but we don't know what it's made of. Dark energy, meanwhile, is the mysterious force that's causing the expansion of the universe to accelerate, defying our expectations of gravity. Unraveling the mysteries of dark matter and dark energy will require a new generation of experiments and observatories, from underground detectors searching for weakly interacting massive particles to space telescopes mapping the large-scale structure of the universe. It's a daunting challenge, but one that could revolutionize our understanding of the cosmos and our place within it. As we continue to explore the frontiers of science, it's worth reflecting on the remarkable journey that brought us to this point. From the dawn of modern science in the 16th century to the cutting-edge discoveries of today, we've come an astounding distance in our quest to understand the universe and our place within it. We've met some of the most brilliant minds in history along the way, from Copernicus and Galileo to Newton and Einstein, Hubble and Hawking. Each of them pushed the boundaries of human knowledge and transformed our view of the cosmos, often in the face of great adversity and opposition. And for every towering figure we've discussed, there are countless other scientists and unsung heroes who contributed to the great edifice of human knowledge, brick by painstaking brick. As we look ahead to the discoveries that await us in the decades and centuries to come, it's impossible not to feel a sense of wonder and excitement. Will we finally unravel the mysteries of dark matter and dark energy? Will we discover life on other worlds, or even make contact with alien civilizations? Will we find a way to unite the theories of quantum mechanics and gravity and arrive at a theory of everything that explains the universe from the smallest subatomic scales to the largest cosmic structures? Only time will tell. But one thing is certain, the story of science is far from over. As long as there are curious minds willing to ask the big questions, and intrepid explorers willing to venture into the unknown, we will continue to push back the frontiers of knowledge and deepen our understanding of the universe we call home. And who knows what revolutionary insights and world-changing discoveries the future may bring. For now, as we come to the end of our journey through the history of science, I invite you to rest your mind and reflect on the wonders we've encountered along the way. From the elegant clockwork of Newton's laws to the mind-bending paradoxes of quantum mechanics, from the birth of the universe in the Big Bang to the dance of galaxies across the cosmic web, we've seen how science has illuminated the beauty and mystery of the cosmos at every scale. So as you drift off to sleep, let's return to the cosmic arena and the perplexing puzzle pieces that make up our universe. While the scientific titans of old laid the foundations, the 20th century ushered in a new era of discovery that would redefine our understanding of reality on the grandest scales and tiniest frontiers. In the early decades of the 1900s, astronomers were grappling with the true extent of the cosmos. Many still believed the Milky Way encompassed the entire universe, but one astronomer sought to shatter that notion. Armed with the mighty 100-inch Hooker telescope at Mount Wilson Observatory in California, Edwin Hubble meticulously studied distant nebulae and variable stars. Through tireless observation and brilliant deduction, Hubble discovered that these nebulae were in fact distinct galaxies far beyond the bounds of the Milky Way. In an instant, our cosmic horizons expanded from a single galaxy to a universe teeming with billions of island worlds. It was as if humanity had been living in a small room their entire lives, only to one day open a door and step into an endless expanse. But Hubble wasn't finished upending our cosmic perspective. Teaming up with Milton Humason, the two researchers examined the spectra of dozens of galaxies, noticing a peculiar shift toward the red end of the spectrum. The more distant the galaxy, the greater its redshift appeared. Hubble and Humason realized this redshift was evidence of galaxies racing away from us in all directions. The unavoidable conclusion: the universe was expanding. This monumental discovery, published in 1929, would shake the foundations of cosmology. A static, eternal cosmos gave way to a dynamic universe with a beginning. As Hubble once remarked, equipped with his 5 senses, man explores the universe around him and calls the adventure science. And what an adventure it had become. Belgian priest and astronomer Georges Lemaitre had been pondering the implications of an expanding universe. If galaxies were flying apart, rewinding the clock would imply the cosmos began in an incredibly dense, compact state. In 1931, Lemaitre proposed that the universe originated from a primeval atom, a cosmic seed that gave rise to all of space and time in a burst of creation. Though controversial at first, this so-called Big Bang theory would gain traction in the coming decades. Further evidence for the Big Bang emerged in 1948, when physicists Ralph Alpha and George Gamow predicted that the early universe would have left behind a faint afterglow, a bath of microwave radiation permeating all of space. This cosmic microwave background, or CMB, would be a smoking gun for the Big Bang model. As fate would have it, the CMB was discovered quite by accident in 1964. While tinkering with a radio receiver at Bell Labs in New Jersey, astronomers Arno Penzias and Robert Wilson detected a persistent hiss that seemed to emanate from every corner of the sky. Perplexed, they ruled out all sources of interference, even evicting a pair of nesting pigeons from the antenna. The mysterious signal, it turned out, was the long-sought echo of creation, the first light of the universe, cooled and stretched across billions of years of cosmic expansion. The discovery of the CMB was a crowning achievement, cementing the Big Bang as the leading model of our universe's origins. But even as we marveled at the grandeur of the expanding cosmos, a new frontier was opening up, a world of the unseen, where ghostly particles flit and dance to the tune of quantum rules. In the 1960s, physicists were hard at work developing the standard model of particle physics, a sort of periodic table of the subatomic realm. They organized the zoos of fundamental particles into categories based on their properties and interactions. Protons and neutrons, once thought indivisible, were now understood to be composed of even smaller units called quarks, as proposed by Murray Gell-Mann and George Zweig in 1964. The standard model proved remarkably successful at explaining and predicting the behavior of particles. But one key piece remained elusive: the Higgs boson. Theorized in 1964 by Peter Higgs and others, this particle was thought to endow all other particles with mass through a sort of cosmic molasses pervading space. Confirming its existence would be a major milestone. The hunt for the Higgs reached a fever pitch in the early 2000s with the construction of the Large Hadron Collider near Geneva, Switzerland. This 27-kilometre, 17-mile ring would accelerate particles to near the speed of light and smash them together, recreating conditions not seen since the Big Bang. If the Higgs existed, the LHC would find it. On July 4th, 2012, the wait was over. In a packed auditorium, physicists announced they had discovered a particle matching the properties of the long-sought Higgs boson. The confirmation was a triumph of theory and experiment, a testament to the power of scientific prediction and human ingenuity. With the Higgs in hand, the Standard Model was complete. But even in this moment of celebration, new mysteries were already beckoning. Indeed, for all the Standard Model's success, it paints an incomplete picture of our cosmos. Observations of galaxies and clusters reveal the visible matter we cherish. Stars, planets, people, accounts for a paltry fraction of the universe. Some unknown substance, dubbed dark matter, appears to outweigh normal matter by a factor of 5. Even more baffling, the expansion of the universe is accelerating, driven by a force scientists call dark energy. Together, dark matter and dark energy are estimated to make up 95% of the cosmos. Their true nature remains one of the deepest mysteries in physics, but even in the darkness, glimmers of light emerge. In 2015, a century after Einstein predicted their existence, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves, ripples in the fabric of space-time itself, the source, the spectacular collision of two black holes over 1 billion light-years away. By listening to the universe in a whole new way, LIGO promises to reveal hidden corners of the cosmos and test theories of gravity in the most extreme environments imaginable. Meanwhile, the search for our cosmic origins presses forward. In 1992, astronomers confirmed the existence of planets orbiting other stars, the first in a flood of exoplanet discoveries that now number in the thousands. With telescopes like Kepler and TESS, we're finding worlds of breathtaking variety, broiling gas giants, Earth-sized rocky planets, even ocean worlds that may harbour alien life. Each new find blurs the lines between science and science fiction. Looking ahead, the James Webb Space Telescope, launched on December 25, 2021, will peer further than ever before, capturing light from the first stars and galaxies to ignite after the Big Bang. Webb will also study the atmospheres of exoplanets, searching for signs of habitability and the chemical fingerprints of life. Its golden eye may be the first to glimpse the shadows of another living world. And so, as you slip softly into slumber, take comfort in the remarkable journey of discovery that brought us to this cosmic eye blink. From the Renaissance visionaries who dared to imagine a sun-centered universe to the unsung heroes who mapped the subatomic and extragalactic frontiers, the torch of scientific progress has passed from generation to generation, illuminating the mysteries of nature and our place within it. Though much remains unknown, the brilliant minds of the past and the eager explorers of today remind us that no question is too daunting, no horizon too distant, if we maintain our sense of wonder and our thirst for knowledge. In an infinite universe, there is infinite room for discovery. As you dream, let your mind wander among the galaxies and quantum fields, the dark matter halos and undiscovered particles. For the story of science is ultimately a human story, a tale of curiosity, perseverance, and the unrelenting search for truth in the face of nature's riddles. And as long as that spirit endures, as long as we keep asking why and how, there's no telling what marvels await us in the undiscovered country beyond the present, a future limited only by the reach of our imagination and the courage of our convictions. The universe is vast and it beckons to us still, inviting us to continue this grand adventure we call science. But for now, let the cosmic background radiation be your lullaby, carrying you on waves of light from the birth of space and time. Rest easy knowing that as long as one mind seeks to unravel the mysteries of nature, the love of discovery can never be extinguished. For in a very real sense, we're all made of star stuff, the atoms in our bodies forged in the crucibles of long-dead suns. We are the universe looking back on itself, embarking on the greatest voyage of self-discovery any species has ever attempted. And though the road ahead is long and the night sky deep, we can take solace in the fact that we've already come so far, one observation and experiment at a time. The most important scientific discoveries are not always the ones that make headlines, but the ones that change how we see ourselves and our place in the grand cosmic tapestry. In that light, perhaps the greatest discovery of all is the realization that we are part of something much larger, an evolving universe of ceaseless change and infinite potential, forever unfolding toward a future beyond our most ambitious imaginings. It's a perspective that's both humbling and stirring, a reminder of our fleeting existence and the preciousness of this pale blue dot we call home. As you drift off to dream, know that you are a participant in the grandest story ever told, the story of a universe coming to know itself through the power of the human mind. And as long as that mind keeps wandering and wondering, the adventure of science will continue, beckoning us ever onward to the horizons of understanding. Good night, and may your dreams be filled with the beauty and mystery of the cosmos, for in the end that's what science is all about, a celebration of the world we inhabit and the unquenchable human spirit that yearns to comprehend it. Rest well, knowing that the journey of discovery continues, even as you slumber beneath the stars. Softly, methodically, the astronomical discoveries of the 20th century began to reveal the true scale and splendor of the cosmos. As telescopes grew larger and more sophisticated, they granted us an unprecedented glimpse into the vastness stretching out beyond our own Milky Way galaxy. In the 1920s, astronomer Edwin Hubble spent countless nights peering through the eyepiece of the mighty 100-inch Hooker telescope perched atop Mount Wilson in California. With painstaking precision, Hubble studied the mysterious spiral nebulae scattered across the sky. Some astronomers believe these hazy spirals were simply clouds of gas and dust drifting within our own galaxy. But Hubble suspected they were something far more profound. Poring over photographic plates, Hubble managed to pick out individual variable stars within several of these spiral nebulae, including the stunning Andromeda Nebula. By carefully measuring how these stars fluctuated in brightness over time, Hubble could determine their distance using a cosmic yardstick discovered by Henrietta Swan Leavitt, called the period luminosity relation. Hubble's calculations revealed a shocking truth. The Andromeda Nebula lay far beyond the bounds of the Milky Way, some 900,000 light-years from Earth. This swirling collection of stars was not a nebula at all, but an entirely separate island universe, a galaxy in its own right, the Andromeda Galaxy. With that discovery, our cosmic horizons expanded in one fell swoop. Hubble continued surveying the sky, and soon realized that galaxies are the true building blocks of the universe, and our Milky Way is but one among countless trillions. As wondrous as this revelation was, Hubble's work soon yielded another groundbreaking find, one that would shake our understanding of the cosmos. Collaborating with Milton Humason, Hubble began measuring the spectra of galaxies, examining the wavelengths of light emanating from them. They expected to see a fairly even mix of blue-shifted and red-shifted spectra, corresponding to galaxies moving randomly relative to us. Instead, Hubble and Humason found that nearly all galaxies exhibited a redshift in their spectra, indicating they were receding away from us. Even more astonishing, the degree of redshift increased with distance. More remote galaxies appeared to be racing away faster than nearer ones. The conclusion was inescapable. The universe itself is expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. In 1929, Hubble and Humason announced their historic discovery of the expanding universe, overturning the long-held notion of a static and unchanging cosmos. The farther a galaxy lies from us, the faster it recedes as space swells between us and it. It was a revelation that would soon inspire even grander theories. Belgian physicist and Catholic priest Georges Lemaitre had been pondering the implications of an expanding universe. Taking the notion to its logical conclusion, Lemaitre proposed that if the universe is expanding now, then it must have been smaller in the past. Extrapolating backwards in time, Lemaitre envisioned the universe contracting down to an extremely hot and dense state he christened the primeval atom. From this initial state, Lemaitre conceived that the universe began in a tremendous burst of expansion, a cosmic genesis that set the galaxies hurtling apart. It was a revolutionary idea that would come to be known as the Big Bang Theory. In 1931, Lemaitre published his daring vision of the origin of the universe, mathematically backing it up using Einstein's theory of general relativity. However, the notion was initially met with skepticism from the scientific community, including Albert Einstein himself, who believed in an eternal and unchanging universe. But observational evidence would soon swing in favour of the Big Bang. Russian-American physicist George Gamow and his student Ralph Alpher picked up on Lemaitre's work and began refining it. If the universe was born in a tremendously hot flash, they reasoned, then as it expanded it would have cooled. Alpher and Gamow calculated that the afterglow of the Big Bang should be detectable even now, as microwave radiation permeating all of space. This relic radiation, if found, would be smoking gun evidence for the Big Bang. In 1948, Alpher and Gamow published their prediction of what came to be known as the cosmic microwave background. As it turns out, this whisper of creation would be discovered entirely by accident. In 1964, Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey, were experimenting with a sensitive horn antenna. But a mysterious hiss kept interfering with their work, a faint but persistent noise that they couldn't seem to get rid of no matter how they adjusted their equipment. Puzzled, Penzias and Wilson checked everything they could think of. They pointed their antenna at New York City to rule out urban interference. They even swept out the pigeon droppings in the antenna horn. Still, the stubborn hiss remained. Penzias and Wilson began to suspect they had stumbled onto something far more extraordinary than pigeon dung. Upon comparing notes with a team of physicists at nearby Princeton University, the truth dawned on them. Penzias and Wilson had serendipitously detected the cosmic microwave background, the long-sought echo of the Big Bang. Their accidental discovery was soon confirmed as the CMB was mapped in detail, fitting precisely the predictions of the Big Bang Theory. Penzias and Wilson shared the Nobel Prize in 1978 for their landmark find. With the discovery of the cosmic microwave background, the Big Bang graduated from speculative theory to accepted scientific fact. It was a profound realization. Our universe had a beginning, a finite age, and from that hot, dense origin, the cosmos has been expanding and cooling for the past 13.8 billion years, giving rise to galaxies, stars, planets, and ultimately us. As the 20th century progressed, astronomers continued to refine the Big Bang theory and probe the evolution of the cosmos. In the 1960s and 70s, the space race between the United States and Soviet Union kicked into high gear, opening up new opportunities for cosmic exploration. In 1977, NASA launched the twin Voyager 1 and Voyager 2 space probes on an epic journey to the outer reaches of the solar system. After executing flybys of Jupiter, Saturn, Uranus and Neptune, the Voyagers pressed onward, speeding toward the boundary between our solar system and interstellar space. In 2012, Voyager 1 made history by crossing that threshold, becoming the first human-made object to enter the space between the stars. 6 years later, Voyager 2 repeated the feat. The Voyager missions, originally intended to study the giant outer planets, had delivered us to the cosmic shoreline where the influence of our Sun gives way to the vast ocean of the Milky Way galaxy. As the Voyagers continue their lonely journeys, they carry an interstellar message in a bottle, the golden record affixed to each probe containing sights, sounds, music, and greetings from Earth. A time capsule of our world, sailing out into the galaxy. While the Voyagers set sail for the stars back on Earth, particle physicists were unravelling the fundamental building blocks of matter. In the 1960s and 70s, researchers developed the Standard Model, a theoretical framework that weaves together the menagerie of subatomic particles and the forces that govern them. The Standard Model organises elementary particles into several families: quarks, leptons and bosons. Quarks, which come in 6 flavours, are the constituents of protons and neutrons and by extension all atomic nuclei. Leptons include familiar particles like the electron, as well as more exotic fare like the muon and neutrino. Bosons are the particles that mediate forces, the most famous being the photon, which carries the electromagnetic force. But as successful as the Standard Model was in accounting for the subatomic world, there was a glaring omission. It provided no explanation for why particles have mass. physicists theorized that a mysterious field, the Higgs field, permeates all of space. As particles travel through the Higgs field, their interactions with it imbue them with a mass. The Higgs field would have a signature particle of its own, the Higgs boson, but detecting it would prove a monumental challenge. In 2008, the Large Hadron Collider near Geneva, Switzerland began its operations. The largest and most powerful particle accelerator ever built, the 16-mile ring of the LHC accelerates protons to nearly the speed of light before smashing them together. These collisions release tremendous amounts of energy, fleetingly recreating the conditions that existed shortly after the Big Bang. If the Higgs boson existed, the LHC would be the machine to find it. After years of gathering and sifting data, the two main experiments at the LHC, ATLAS and CMS, announced a monumental discovery on July 4, 2012. They had detected a new particle with a mass of around 125 GeV, consistent with the long-sought Higgs boson. Further data confirmed the particle's identity, filling in the final missing piece of the Standard Model. For the first time, physicists could explain why matter has mass. Even as particle physicists were celebrating their Higgs triumph, across the Atlantic another long-awaited discovery was brewing. The first direct detection of gravitational waves. These ripples in the fabric of spacetime were predicted by Einstein's theory of general relativity a century earlier. But Einstein doubted they would ever be detected, as the stretching and squeezing of space they produce is so mind-bogglingly small. But incredibly sensitive instruments called laser interferometers, built in the United States as part of the LIGO project, Laser Interferometer Gravitational Wave Observatory, would finally capture these elusive waves. On September 14, 2015, LIGO's detectors in Louisiana and Washington state registered a signal, a cosmic chirp lasting just a fraction of a second. Analysis revealed this ripple in spacetime was produced by the cataclysmic merger of two black holes, some 1.3 billion light-years away. The LIGO detection was a technical tour de force, measuring a spacetime distortion just 1/10,000th the width of a proton. It opened up a whole new way of observing the universe. Just as radio telescopes allowed us to see the cosmos in radio waves, and X-ray telescopes unveiled the X-ray universe, gravitational wave observatories let us listen in on the soundtrack of gravity, the cymbal crashes of colliding black holes and the drumbeats of dancing neutron stars. In the years since that first detection, LIGO and its European counterpart Virgo have heard dozens more gravitational wave events, ushering in the era of multi-messenger astronomy. By combining gravitational wave data with observations in electromagnetic radiation, we're gaining new insights into the most extreme events in the universe. Even as we probe the subatomic and the ultramassive, the next generation of observatories promises to shed light on the birth and evolution of galaxies. In December 2021, the James Webb Space Telescope, the largest and most complex observatory ever sent to space, began its mission to unfold the history of the cosmos. With a primary mirror 21 feet across and a sunshield the size of a tennis court, the James Webb is an engineering marvel. Orbiting the Sun 1 million miles from Earth, the telescope will peer back to the dawn of the first galaxies, witnessing cosmic structure emerging from the primordial soup. Webb will also study the atmospheres of nearby exoplanets, searching for signs of potential habitability, and maybe even hints of alien biology. With over 5,000 exoplanets discovered and counted, and estimates of trillions more in the Milky Way, the age-old question of whether we're alone in the universe feels more pressing than ever. Even as powerful as the James Webb Space Telescope is, it's only the beginning of a new wave of observatories. Astronomers are dreaming up even larger space telescopes, as well as mega observatories on the ground like the extremely large telescope under construction in Chile. With a primary mirror 128 feet across, the ELT will capture the cosmos in unprecedented detail, perhaps even imaging Earth-like planets around other stars. But even as we build bigger and better telescopes, we've come to realize that all the normal matter we can see, galaxies, stars, planets, and us, makes up only a small sliver of the universe. A far larger share, some 85%, is composed of invisible dark matter, detectable only by its gravitational pull on the visible. Even more baffling, nearly 70% of the cosmos is made of a mysterious entity called dark energy, a repulsive force that is causing the expansion of the universe to accelerate. We don't yet know what dark matter and dark energy are, but solving these cosmic riddles may hold the key to understanding the ultimate fate of the universe. Will the cosmos keep expanding forever, or will dark energy eventually tear the very fabric of space-time asunder in a big rip? Or could dark energy dissipate, reversing the expansion and causing a big crunch? These are the questions that tantalize cosmologists as they ponder the distant future and ultimate destiny of our universe. As we contemplate these grand cosmic mysteries, it's worth pausing a moment to reflect on the long path of discovery that led us here. From the first glimmerings of the scientific revolution in the 16th century to the triumphant edifice of modern science we've constructed today, the journey has been one of ever-increasing wonder and humility. With each new discovery, each page of nature's tome deciphered, we've been reminded again and again of the astonishing scale and beauty of the cosmos we find ourselves in. A universe far vaster, older, and more filled with marvels than our ancestors could have ever imagined. And yet, the scientists who built this cathedral of understanding were humans just like us. Men and women of passion and perseverance, curiosity and conviction. From Galileo braving the Inquisition to uphold the truth, to Newton laying the foundations of classical physics, to Einstein reimagining space and time, to Hubble revealing a universe of galaxies, these visionaries expanded our horizons and brought the cosmos within our collective grasp. Along the way, there have been countless other heroes, most of them unsung, the assistants and apprentices, the technicians and tinkerers, the teachers and dreamers. Science is a massively collaborative human endeavour, with each researcher adding their verse to the grand poem of nature, composing meaning from its mysterious meter. Looking back, we can only marvel at how far we've come in our quest to understand this amazing universe we call home. And yet, with every question answered, new and deeper ones arise. We've traced the history of the universe back to the Big Bang, but what came before that? What breathed fire into the equations and set the cosmos into motion? Is our universe the only one, or are we part of a grander multiverse? These are the questions that will animate the scientists of the 21st century and beyond, as they take up the torch and continue the journey. With breathtaking discoveries on the horizon, from gravitational wave astronomy to quantum computing to the search for alien life, the coming decades promise to be a thrilling time in our ongoing dance with nature. And yet, even as we push the boundaries and sail uncharted cosmic seas, we should never lose sight of the profound beauty and privilege of simply being, of having a mind capable of asking these deep questions, and a heart that quickens with each new revelation. As you drift off to sleep, ponder for a moment your place in the grand tapestry of the universe. 13.8 billion years in the making, a cosmos so vast and ancient it defies imagination, and yet, here you are, a sentient speck of stardust, an heir to the light, capable of contemplating it all. There is perhaps no greater gift than this, the capacity for wonder, the ache to understand, and the realization that we are part of something immense and achingly beautiful. So rest easy, dear dreamer, and let the soft breeze of nature's mysteries lull you into peaceful slumber. For tomorrow is another day to revel in the magic of existence, to ask the burning questions, and to drink deeply from the cup of cosmic wonder. The universe may be vast and inscrutable, but it is also our home, and there is no greater adventure than trying to understand its innermost workings. Good night, and may your dreams be filled with the sweet nectar of the cosmos. And so the spark of electricity kindled a new age of discovery, as experimentalists continued probing this mysterious force in labs and workshops across Europe and the young United States. Benjamin Franklin, in between his duties as a statesman, printer and postmaster, found time to conduct his own ingenious electrical experiments. On a stormy summer's day in 1752, Franklin ventured out into a field as lightning crackled overhead. With the help of his son, he launched a silk kite with a pointed wire attached to the top. As the kite soared, Franklin felt the fibres of the hemp string bristle and stand erect, an unmistakable sign that it was conducting an electrical charge from the thunderclouds above. Though the tale of Franklin narrowly escaping electrocution that day may be somewhat embellished, there's no doubt his bold experiment provided clear evidence that lightning was indeed electrical in nature. Meanwhile in Italy, anatomist Luigi Galvani noticed that dissected frogs' legs would twitch when touched by metal instruments, as if suddenly reanimated. He mistakenly believed this to be evidence of an animal electricity innate to living tissue. But Galvani's friend and rival, physicist Alessandro Volta, suspected the true cause lay in the contact between two different metals. Through a series of experiments in the 1790s, Volta proved that electricity could be generated by joining copper and zinc electrodes, separated by brine-soaked paper discs. When the discs were stacked and connected by a wire, an electric current flowed continuously through the circuit. Volta had invented the first electric battery, which he called a pile, the prototype for the world-changing technology that today powers everything from smartphones to pacemakers. As the 19th century dawned, scientists grew increasingly convinced that electricity and magnetism were somehow intricately linked. Danish physicist Hans Christian Ørsted was lecturing to his students in 1820 when he noticed a compass needle being deflected by a nearby wire conducting an electric current. Ørsted had stumbled upon clear evidence that electricity could produce a magnetic field. Within weeks, news of his discovery spread across Europe, igniting a frenzy of research into the relationship between these two primal forces. Building on Ørsted's work, English scientist Michael Faraday made a series of groundbreaking discoveries in the new field of electromagnetism. Faraday was a bookbinder by trade with little formal education, but his genius for experimentation earned him a position as a lab assistant at London's Royal Institution. In 1831, he found that moving a magnet through a coil of wire generated an electric current, the principle behind the electric generators that power our world to this day. Faraday went on to develop the first electric motor and formulate the concept of magnetic fields, pictured as invisible lines of force flowing around a magnet. A modest, deeply religious man, Faraday saw divine beauty in the unity of nature that his discoveries revealed. It was the Scottish physicist James Clerk Maxwell who wove Faraday's intuitions into a rigorous mathematical theory. As a young man, Maxwell was fascinated by the strange properties of polarized light, coloured ribbons that swirl around objects when seen through special filters. In a flash of insight, he realized that Faraday's electric and magnetic field lines could be translated into mathematical equations. Maxwell's equations, first published in completed form in 1865, showed that electricity and magnetism were two sides of the same coin, a unified electromagnetic force that propagated through space as waves travelling at the speed of light. With a start, Maxwell understood that light itself was an electromagnetic wave. Radio waves, gamma rays, the rainbow of visible colours, all were manifestations of the same fundamental force, differing only in frequency and wavelength. The discovery hinted at a profound interconnectedness in nature, a harmony of matter and energy that scientists are still unravelling to this day. As the 19th century progressed, chemists busied themselves with cataloguing and classifying the bewildering variety of substances that made up the material world. Building on Lavoisier's precise accounting of chemical reactions, they set out to identify the pure elementary ingredients that combine to form all known compounds. By mid-century, dozens of elements had been discovered, familiar substances like oxygen, nitrogen and carbon, but also reactive metals like sodium and potassium pulled from caustic salts. The race was on to fill in the gaps in this periodic procession, from lightest to heaviest. The key to deciphering the hidden order of the elements came from an unlikely source, a young Russian chemistry professor named Dmitry Mendeleev. Mendeleev was a big, boisterous man with a flowing beard who loved card games and frequently quarrelled with his colleagues. But he also possessed a powerful intuition for the unity of nature. In 1869, while working on a chemistry textbook, Mendeleev decided to arrange the known elements in a grid, ordered by their atomic weight but also grouped by shared chemical properties. When he placed elements with similar characteristics in vertical columns, a striking pattern emerged, a periodic table in which each row, or period, repeated the properties of the one above. Mendeleev's periodic table was more than just an organizational tool. It was a roadmap to discovery. By leaving blank spaces where he believed unknown elements would fit, he was able to predict their atomic weights and chemical behavior with uncanny accuracy. When the new elements gallium and germanium were discovered in the 1870s, they slotted perfectly into the gaps Mendeleev had left for them, stunning the scientific world. The periodic table had revealed that the elements were not scattered at random, but followed a deep underlying order, a symphony of matter waiting to be decoded. As the 19th century drew to a close, physicists made an astonishing discovery that hinted at the existential drama playing out at the smaller scales of matter. In 1896, French physicist Henri Becquerel found that certain uranium salts emitted mysterious rays that could fog photographic plates, even when wrapped in thick black paper. Becquerel's doctoral student, a brilliant young Polish scientist named Marie Curie, grew captivated by this strange phenomenon. Together with her husband Pierre, Marie Curie threw herself into studying these uranium rays, which she christened radioactivity. The Curies soon traced the radioactivity to two new, intensely radioactive elements, which they painstakingly extracted from tons of uranium ore and named polonium and radium. In 1903, they shared the Nobel Prize in Physics with Becquerel for their discovery. Marie Curie became the first woman to win a Nobel, and would win a second in chemistry in 1911 for her studies of radium and its compounds. Despite the acclaim, her pioneering research came at a tragic cost. After years of handling radioactive materials with her bare hands, she died of aplastic anemia, likely caused by radiation exposure in 1934. The Curies had glimpsed the incredible atomic energy bound up in unstable, radioactive elements like radium and uranium. As physicists continued to probe the structure of the atom in the early 20th century, they found that this energy originated in the nucleus at its heart. In 1917, Ernest Rutherford became the first to split the atom, transmuting nitrogen into oxygen by bombarding it with alpha particles in his laboratory in Manchester. The world would soon learn the terrifying destructive potential that could be unleashed by splitting heavy atoms like uranium. But that apocalyptic chapter of atomic science was yet to come. For decades, physicists had modelled the atom as a miniature solar system, with electrons whizzing around a dense central nucleus in planet-like orbits. But as experiments probed the properties of electrons more closely, it became clear that this tidy picture was far too simplistic. Electrons seemed to behave as both particles and waves, with a maddeningly indeterminate position and velocity. In 1913, the Danish physicist Niels Bohr proposed that electrons could only occupy fixed energy levels within the atom, leaping instantaneously between orbits like fleas. When an electron fell to a lower energy level, it would emit a photon of light with a specific frequency, explaining the colourful line spectra long observed when elements were heated. Bohr's quantum model of the atom was a crucial break from the clockwork determinism of classical physics, but was still only a rough approximation of the bizarre reality. In 1925, the Austrian physicist Erwin Schrödinger formulated a more complete quantum theory by describing electrons as waves rather than particles. According to Schrödinger's wave equation, an electron's position could only be expressed in terms of probability, smeared out in a fuzzy orbital around the nucleus. When you made a measurement, the wave function collapsed to a single point, but it was impossible to know the electron's precise location beforehand. This strange, probabilistic view of the subatomic world was a radical departure from the clear-cut cause and effect of Newtonian physics. The unsettling implications of quantum theory were further cemented by the German physicist Werner Heisenberg in 1927. Heisenberg showed that the more precisely you tried to pin down an electron's position, the more uncertain its momentum became, and vice versa. This uncertainty principle meant there was an inherent fuzziness to the subatomic realm, a limit to how much we could ever know about particles on the smallest scales. Nature, it seemed, was fundamentally indeterminate, a game of chance played out in the strange arena of the atom. Despite these disorienting discoveries, physicists charged ahead, driven by the tantalizing prospect of a unified theory of matter and energy. The next great leap forward came from an unlikely source, a young patent clerk in Switzerland named Albert Einstein. In 1905, Einstein published 4 groundbreaking papers that would revolutionize our understanding of space, time, and the nature of light. In his paper on the photoelectric effect, Einstein proposed that light was composed of particle-like photons whose energy was proportional to their frequency. This daring idea, which built on Max Planck's earlier notion of light quanta, explained the puzzling way certain metals emitted electrons when struck by light. For this insight, Einstein would be awarded the Nobel Prize in 1921, but Einstein's most revolutionary paper of 1905 introduced his special theory of relativity, which rewrote the laws of motion for objects travelling at high speeds. Einstein did away with the notion of absolute space and time, showing that both were relative depending on the motion of the observer. Moving clocks ran slow, he predicted, and objects shortened in the direction of travel. The theory climaxed in the famous equation E=mc², which revealed the enormous energy that could be released by converting matter into pure energy. Overnight, Einstein became a global scientific celebrity, the wild-haired sage unravelling the mysteries of the universe. Quantum theory would later show his notion of quanta applied to all matter, not just light. In 1924, Louis de Broglie argued that electrons and other particles also had wave-like properties, a strange duality that remains a cornerstone of quantum physics. Einstein, for his part, was deeply uncomfortable with the probabilistic nature of quantum mechanics, insisting that God does not play dice. He spent his later years in a fruitless quest for a unified field theory, which he hoped would restore determinism and rationality to the cosmos. But the quantum genie could not be put back in the bottle. As the 20th century progressed, physicists continued to chart the surreal subatomic landscape of electrons, protons, and neutrons, smashing particles together in ever more powerful accelerators to glimpse exotic new forms of matter. In the process, they pushed the boundaries of human knowledge to the very edge of the unknowable, the strange shimmering boundary where reality dissolves into ghostly probabilities and phantasms. And yet, even as they mapped the fundamental building blocks of nature, 20th century physicists were grappling with an even more profound mystery, the ultimate origin and fate of the universe itself. In the 1920s, American astronomer Edwin Hubble, peering through the world's largest telescope atop Mount Wilson in California, discovered that the Milky Way was just one of countless island universes strewn across the inky depths of space. As Hubble trained his telescope on these distant galaxies, he noticed something peculiar. Their light was shifted towards the red end of the spectrum, stretched out like the Doppler siren of a receding ambulance. The further away the galaxy, the greater its redshift, implying it was racing away from us at tremendous velocity. In a flash of insight, Hubble realized the universe must be expanding like a balloon, carrying the galaxies along with it as it inflated ever outwards into the void. Hubble's discovery was the first observational evidence for the Big Bang theory of cosmology, which proposed that the universe had begun in a state of incredible heat and density, exploding outwards and cooling over billions of years to form the galaxies we see today. The theory was pioneered by Russian physicist Alexander Friedmann and Belgian priest Georges Lemaitre in the 1920s, based on Einstein's equations of general relativity. If the expansion could be traced backwards in time, they realized the universe must have had a beginning, a primordial day without yesterday, as Lemaitre poetically put it. This notion of a universe with a definite starting point was deeply unsettling to many scientists, who clung to the classical belief in an eternal, unchanging cosmos. Even Einstein was skeptical at first, dismissing Friedmann's dynamical solutions as suspicious. But as the evidence mounted, he was forced to concede that the universe appeared to be expanding after all. The final definitive proof of the Big Bang came in 1964 from an unlikely source, two radio astronomers in New Jersey named Arno Penzias and Robert Wilson. Penzias and Wilson were trying to map radio signals from the Milky Way using a sensitive antenna built for satellite communications, but no matter where they pointed the dish, they kept picking up a faint, persistent hiss that wasn't supposed to be there. At first they thought it might be a problem with the antenna, or even droppings from nesting pigeons, but after months of careful calibration, they realized the signal was real, a cosmic microwave background radiation that filled the entire sky. At the same time, a team of physicists at Princeton had predicted that the fading afterglow of the Big Bang should be detectable as a nearly uniform microwave glow. When they heard about Penzias and Wilson's discovery, they immediately recognized it as the smoking gun for the Big Bang theory. For their serendipitous find, Penzias and Wilson would share the 1978 Nobel Prize in Physics. The cosmic microwave background became a window into the earliest moments of the universe, a baby picture of the cosmos as it existed just 380,000 years after the Big Bang. By carefully mapping subtle temperature variations in the CMB, cosmologists could test their theories of how the universe evolved from a formless sea of energy to the intricate web of galaxies we see today. In recent decades, satellites like COBE, WMAP and Planck have measured the CMB with ever greater precision, providing crucial evidence for the reality of the Big Bang and the mysterious dark matter and dark energy thought to make up the lion's share of the universe. And so, from the subatomic realm of quarks and leptons to the cosmic expanse of galaxy clusters and dark matter halos, 20th century physicists painted an astonishing new picture of the physical world, a universe of staggering scale and complexity, yet governed by an elegant mathematical order. At the smallest scales, quantum mechanics traced the fuzzy trajectories of particles dancing to a probabilistic tune. At the largest scales, general relativity wove space and time into a seamless fabric warped by the gravity of stars and galaxies. And at the frontiers of the very big and the very small, scientists glimpsed tantalizing new puzzles: dark matter and dark energy, quantum entanglement and black hole firewalls that hinted at even deeper mysteries waiting to be unlocked. As we stand on the brink of a new scientific renaissance, it's worth reflecting on how far we've come since Galileo first pointed his telescope skyward and Newton teased out the invisible laws of motion. In just a few short centuries, human ingenuity has laid bare the inner workings of the atom, the architecture of the cosmos, and the mathematical underpinnings of space and time. We've discovered new forms of energy and matter, from electromagnetism to radioactivity to the Higgs boson, that have transformed our world in ways the ancients could scarcely imagine. And we've launched satellites and space probes beyond the solar system, casting our instruments into the void in a quest to find our place in the wider universe. Yet for all the triumphs of modern science, we are left with the humbling realization that we have only begun to scratch the surface of nature's mysteries. As we peer deeper into the subatomic world and further back in cosmic time, we confront ever more perplexing enigmas that strain the limits of human comprehension. We now know that the visible universe, the stars and galaxies that light up the night sky, makes up a paltry 5% of the total cosmic energy budget. The rest is in the form of invisible dark matter and dark energy, whose true nature remains one of the great unsolved problems in physics. We've discovered thousands of planets orbiting distant stars hinting at the potential for life beyond Earth, but the question of whether we're alone in the universe continues to haunt us, and we've traced the history of the cosmos back to within a billionth of a second of the Big Bang, but the ultimate origin of space and time remains shrouded in uncertainty. These are the challenges that will define the next great age of scientific discovery, an age of quantum computers and gravitational wave observatories, of Mars rovers and exoplanet explorers, of ever bolder efforts to unlock the secrets of the universe on the smallest and grandest of scales. As we stand on the cusp of this new scientific frontier, it's impossible not to feel a sense of awe at the wonders that await us. Will we discover new particles beyond the standard model that, in the early 1900s, a young German physicist named Max Planck found himself grappling with a problem that threatened to upend the very foundations of physics? At the time, scientists believed that hot objects should emit an infinite amount of energy, an absurdity known as the ultraviolet catastrophe. But as Planck studied the perplexing behaviour of light and heat, he stumbled upon a radical idea that would change our understanding of the universe forever. In a stroke of brilliance, Planck proposed that energy was not emitted in a continuous flow, but rather in discrete packets he called quanta. It was a bold claim, flying in the face of centuries of scientific thought. But the more Planck investigated, the more he became convinced that this strange concept of quantized energy was the key to solving the ultraviolet catastrophe. Little did Planck realize that his groundbreaking work would pave the way for an entirely new branch of physics called quantum mechanics. His ideas about energy quanta would soon capture the imagination of another young physicist named Albert Einstein, who would build upon Planck's foundation to make some of the most remarkable discoveries of the 20th century. Born in 1879 in Ulm, Germany, Einstein was an inquisitive child with a rebellious streak. As a teenager, he voraciously read scientific papers and grew fascinated by the mysteries of light, space, and time. In 1905, while working as a patent clerk in Bern, Switzerland, the 26-year-old Einstein would have an astonishing outpouring of creativity that would forever alter the course of physics. That fateful year, which scientists now refer to as Einstein's miracle year, or annus mirabilis, the young physicist published 4 groundbreaking papers, each of which could have earned him a Nobel Prize. In the first paper, Einstein proposed that light could behave not only as a wave, but also as a particle, an idea that built directly on Planck's concept of energy quanta. Einstein used this insight to explain a baffling phenomenon called the photoelectric effect, where certain metals emit electrons when struck by light. His elegant solution would eventually earn him the Nobel Prize in 1921. But Einstein was just getting started. In his second paper that year, he delved into the tiny, jittering motions of particles suspended in fluid, known as Brownian motion. By calculating the statistical fluctuations of these particles, Einstein provided concrete evidence for the existence of atoms and molecules, which some scientists still doubted at the time. His rigorous mathematical analysis helped prove once and for all that matter was made up of discrete building blocks, just as Planck had shown for energy. Einstein's third and fourth papers of 1905 were even more revolutionary, laying the groundwork for his famous theories of relativity. In the first of these, Einstein introduced the mind-bending concept that time was not absolute, but rather could stretch or contract depending on the relative motion between an observer and an object. Clocks on Earth, he showed, tick at a different rate than clocks on a fast-moving train. It was a radical reimagining of space and time. Later that same year, Einstein published the equation that would become synonymous with his name and forever shape our understanding of the universe, E equals mc squared. This elegantly simple formula showed that energy and matter were two sides of the same coin, that a staggering amount of energy could be unleashed from just a tiny amount of matter. Here was the key to unlocking the secrets of stars, nuclear reactions, and the very origins of the universe itself. Einstein's miraculous discoveries in 1905 sent shockwaves through the scientific community and established him as one of the greatest minds in history. But even as his revolutionary ideas took hold, other scientists were hot on his heels, racing to expand our understanding of the strange and spellbinding quantum world. In 1924, a young French aristocrat and physicist named Louis de Broglie made a wild, seemingly preposterous suggestion. If light could behave as both a wave and a particle, as Einstein had shown, then perhaps matter could as well. It was an audacious leap of logic, but one that would soon be spectacularly confirmed in laboratories around the world. De Broglie's hypothesis implied that electrons, protons, and other subatomic particles, which had always been thought of as solid little spheres, actually possessed wave-like properties. The young Frenchman's ideas caught the attention of an Austrian physicist named Erwin Schrödinger, who set out to mathematically describe the strange wave-particle duality of matter. In 1926, Schrödinger published what would become one of the most important equations in all of physics, the Schrödinger wave equation. This formidable-looking string of symbols and Greek letters allowed scientists to calculate the probability of finding a subatomic particle in a particular location, but it also revealed the deeply counterintuitive nature of the quantum world. According to Schrödinger's equation, particles didn't have definite positions or velocities until they were observed or measured. Prior to measurement, they existed in a hazy state of probability, smeared out across multiple possible locations. It was as if the act of observing a particle somehow forced it to choose a definite state, a phenomenon that came to be known as wave function collapse. This bizarre concept of quantum indeterminacy would later be enshrined in Werner Heisenberg's famous uncertainty principle, which showed that the more precisely you know a particle's position, the less precisely you can know its momentum and vice versa. It was a fundamental limit on our ability to know the world, a built-in fuzziness in the fabric of reality. As scientists grappled with the strange and spooky implications of quantum mechanics in the early 20th century, another revolution was brewing in our understanding of the universe on the grandest of scales. A quiet, unassuming American astronomer named Edwin Hubble was about to make a discovery that would change our cosmic perspective forever. In the 1920s, most astronomers believed that our Milky Way galaxy was the full extent of the universe. The distant, fuzzy spiral shapes that they could see through their telescopes were thought to be swirling clouds of gas within our own galaxy. But Hubble, using the powerful new 100-inch Hooker telescope at Mount Wilson Observatory in California, was about to prove them spectacularly wrong. As Hubble peered deep into the night sky, he noticed something peculiar about those spiral nebulae. Many of them contained strange, pulsating stars called Cepheid variables, which astronomers had recently learned could be used as standard candles to measure cosmic distances. By carefully observing these flickering stars, Hubble calculated that the nebulae were astonishingly far away, much too distant to be part of the Milky Way. With mounting excitement, Hubble realized that those swirling shapes were not gas clouds at all, but rather entire galaxies unto themselves, each containing billions of stars. Our Milky Way, it turned out, was just one of countless island universes adrift in a vast cosmic sea. Hubble's discovery in the 1920s was a stunning revelation, one that suddenly made the universe seem incomprehensibly bigger than anyone had ever imagined. But Hubble wasn't finished. As he continued to measure the distances to galaxies, he noticed something even more remarkable. The farther away a galaxy was, the faster it appeared to be moving away from us. The light from distant galaxies was consistently shifted toward the red end of the spectrum, a telltale sign that they were rapidly receding. It was as if space itself were expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. This astonishing discovery, known as Hubble's law, would provide the first observational evidence for the Big Bang theory, and forever change our understanding of the origin and evolution of the universe. But it would take the brilliant insights of a young Belgian priest and astronomer named Georges Lemaître to piece together the full cosmic puzzle. In 1927, 2 years before Hubble published his groundbreaking observations, Lemaître had already proposed a revolutionary idea that the universe began as an incredibly dense primeval atom that exploded outward in a massive burst of expansion. Lemaître's theory, which he called the hypothesis of the primeval atom, or the cosmic egg, was a radical departure from the prevailing belief in a static, eternal universe. At first, many scientists were skeptical of Lemaître's ideas, including Albert Einstein himself. But as Hubble's observations of an expanding universe became more widely known, Lemaître's theory began to gain traction. In 1931, Lemaître published a seminal paper in the scientific journal Nature, arguing that the expansion of the universe could be traced back to a single originating event, what we now call the Big Bang. According to Lemaître's calculations, the universe began in an extremely hot and dense state, packed with energy and subatomic particles. As the universe rapidly expanded and cooled, these particles began to form into the first simple atoms, which later coalesced into stars and galaxies under the pull of gravity. It was a sweeping and poetic vision of cosmic evolution, one that would capture the imagination of scientists for generations to come. Over the following decades, physicists and astronomers worked feverishly to test and refine the Big Bang theory. In 1948, Ralph Alpher and George Gamow predicted that the intense heat of the early universe should have left behind a faint afterglow of microwave radiation, permeating all of space. This cosmic microwave background, or CMB, would be a smoking gun for the Big Bang, a relic of our universe's fiery birth. It would take another 16 years for the CMB to be detected quite by accident. In 1964, 2 young radio astronomers named Arno Penzias and Robert Wilson were puzzling over a mysterious hiss coming from their antenna at Bell Labs in New Jersey. The pair had meticulously ruled out all possible sources of interference, from nearby radar stations to the droppings of pigeons nesting in their telescope. No matter what they tried, the stubborn hiss remained. Penzias and Wilson soon realized that the mysterious signal was coming from every direction in the sky, with almost perfect uniformity. It wasn't interference at all, but rather the faint afterglow of the Big Bang itself, just as Alpha and Gamow had predicted. The discovery of the CMB was a stunning confirmation of the Big Bang theory, and earned Penzias and Wilson the Nobel Prize in Physics in 1978. As scientists marveled at the newfound evidence for our universe's explosive origins, a new era of cosmic exploration was dawning. In the 1960s, at the height of the Cold War space race between the United States and the Soviet Union, NASA began an ambitious program to send robotic probes to study the planets of our solar system up close. The first successful planetary mission was Mariner 2, which flew by Venus in 1962 and revealed that our neighbouring world was a scorching hellscape, with surface temperatures hot enough to melt lead. But it was the Mariner 4 spacecraft's historic flyby of Mars in 1965 that truly captured the world's imagination. As the probe beamed back the first close-up images of the red planet's cratered surface, it overturned romantic notions of Martian canals and vegetation, revealing a barren, lifeless world. These early planetary missions set the stage for one of the most audacious and iconic space explorations of all time, the Apollo program, which aimed to land humans on the Moon. On July 20th, 1969, as an estimated 650 million people watched on television, astronauts Neil Armstrong and Buzz Aldrin descended from their lunar module onto the Sea of Tranquility, becoming the first humans to set foot on another world. As Armstrong famously declared, "That's one small step for man, one giant leap for mankind." The Apollo 11 moon landing was a crowning achievement of human ingenuity and a powerful symbol of our species' restless drive to explore and discover. Over the next 3.5 years, a total of 12 astronauts would walk on the moon, conducting scientific experiments, collecting samples, and pushing the boundaries of what was thought possible. But even as humans took their first tentative steps on another world, robotic explorers were voyaging much farther afield. In 1977, NASA launched 2 daring missions to study the outer reaches of our solar system, Voyager 1 and Voyager 2. These twin probes, each carrying a gold-plated record of Earth sounds and images, set out on a grand tour of the gas giant planets Jupiter, Saturn, Uranus, and Neptune. As the Voyager probes beamed back stunning images of Jupiter's turbulent atmosphere and Saturn's shimmering rings, they revealed the breathtaking diversity and beauty of worlds that had previously been little more than fuzzy disks in astronomers' telescopes. At Jupiter, Voyager 1 discovered the planet's Great Red Spot was an enormous, centuries-old storm bigger than the Earth itself. The probe also captured the first detailed images of Jupiter's 4 large Galilean moons, including the strange, cracked icy surface of Europa. After their Jupiter flybys, the Voyager probes continued on to Saturn, where they made a string of remarkable discoveries. Voyager 1 found that Saturn's rings were not solid bands, but rather made up of countless individual particles of ice and rock, ranging in size from tiny grains to large boulders. The spacecraft also revealed the intricate braided structure of the rings and the delicate spokes that seemed to rotate within them. Perhaps most intriguing of all was Voyager 1's discovery of volcanoes erupting on Io, one of Jupiter's moons. It was the first time active volcanoes had been seen on another world, hinting at the incredible geological diversity of the solar system. The Voyager probes would go on to study Uranus and Neptune in the late 1980s, revealing 2 strikingly blue ice giant planets whose strange magnetic fields and canted rotational axes set them apart from their gas giant cousins. After completing their primary missions, Voyager 1 and 2 kept on going, speeding toward the edge of the solar system on a one-way journey into the unknown. In 2012, Voyager 1 made history by becoming the first human-made object to enter interstellar space, the vast expanse between the stars. As of 2021, both Voyager probes are still sending back data from more than 14 billion miles away, a testament to the incredible ingenuity and durability of these robotic explorers. As the Voyager probes ventured into the cosmic ocean, a new era of discovery was unfolding back on Earth. In the late 20th century, physicists were closing in on a long-sought dream, a theory of everything that would unite all the fundamental forces of nature into a single, elegant framework. At the heart of this quest was the Standard Model of particle physics, a stunningly successful theory that classified the building blocks of matter into tidy groups and described their interactions through the exchange of force-carrying particles. Developed in the 1960s and 1970s, the Standard Model organized the subatomic world into a periodic table of sorts, with quarks and leptons as the basic units of matter, and bosons mediating the forces between them. But as powerful as the Standard Model was, physicists knew it was incomplete. For one thing, it didn't include gravity, the weakest of the 4 fundamental forces but the one that shapes the universe on the grandest scales. Einstein's general theory of relativity, which described gravity as the curvature of space-time, seemed fundamentally incompatible with the Standard Model's quantum mechanical description of the other forces. There were other gaps in the Standard Model as well. For decades, physicists had puzzled over why certain particles had mass, while others, like photons, were massless. According to the Standard Model, the W and Z bosons that carry the weak nuclear force should have been massless, like the photon that carries the electromagnetic force. But experiments showed that the W and Z bosons did have mass, and quite a lot of it. Something else had to be giving these particles their heft. In 1964, a young British physicist named Peter Higgs proposed a solution to this mass conundrum. Higgs suggested that the universe was permeated by an invisible field, similar to an electromagnetic field that interacted with particles and gave them their mass. According to Higgs's theory, the more strongly a particle interacted with this field, the more massive it would be. Higgs's idea was elegant and compelling, but there was one problem. The field was purely theoretical. To prove it existed, physicists would have to find the telltale particle that was thought to emerge from it, the Higgs boson. But the Higgs boson, if it existed at all, would be incredibly massive and short-lived, requiring enormous energies to produce in particle colliders. The hunt for the Higgs boson became a holy grail of particle physics, a decades-long quest that would ultimately require the construction of the largest and most powerful particle accelerator ever built, the Large Hadron Collider, LHC, at CERN in Geneva, Switzerland. With a circumference of 27 kilometers and the ability to accelerate protons to nearly the speed of light, the LHC was a true marvel of human engineering and scientific ambition. On July 4th, 2012, after years of painstaking work and countless trillions of proton collisions, physicists at the LHC made a momentous announcement. They had discovered a new particle with a mass of around 125 billion electron volts, consistent with the long-sought Higgs boson. The news was met with cheers and champagne toasts around the world, as scientists hailed the completion of the Standard Model and the dawn of a new era in particle physics. The discovery of the Higgs boson was a triumph of human curiosity and persistence, the culmination of a 50-year. As we reflect on the revolutionary insights of Einstein's Annus Mirabilis, it's astounding to consider the sheer intellectual leap his ideas represented. In a single year, this unassuming patent clerk forever altered our conceptions of space, time, mass, and energy. His brilliance would illuminate physics for generations to come. Einstein's groundbreaking papers sent ripples through the scientific community as physicists grappled with the mind-bending implications of special relativity, the notion that space and time were intertwined, that the passage of time itself was relative, challenged long-held assumptions about the very fabric of the universe. No longer could space and time be considered the rigid, immutable stage upon which the great dance of the cosmos unfolded. Einstein had revealed their fluid, malleable nature. Yet even as Einstein radically reshaped our understanding of space-time, other scientists were uncovering the bizarre behavior of nature's tiniest components. The orderly, deterministic universe envisioned by Newton was giving way to a realm of uncertainty and probability, where subatomic particles defied intuition and flirted with the impossible. In 1924, French physicist Louis de Broglie put forth a bold hypothesis. If light could behave as both wave and particle, could the same be true of matter? De Broglie proposed that all matter, from electrons to baseballs, possessed a wave-like nature. It was a stunning idea, one that extended the quirky duality of light to the entire physical world. Austrian physicist Erwin Schrödinger built upon de Broglie's concept, devising a mathematical equation in 1926 to describe the wave-like behavior of matter. The Schrödinger wave equation became a cornerstone of the new science of quantum mechanics, enabling physicists to calculate the probability of a particle's location or velocity. No longer could an electron be pinpointed with certainty. It existed in a haze of probability until measured. Meanwhile, German physicist Werner Heisenberg was grappling with the inherent limits of measurement at the quantum scale. His uncertainty principle, formulated in 1927, showed that the more precisely you measured a particle's position, the less certainty you could have about its momentum and vice versa. It was a fundamental limit on knowledge, woven into the very fabric of reality. Imagine the astonishment of physicists as they confronted this strange new world, where particles behaved like waves and certainty gave way to probability. The classical physics of Newton and Galileo, for all its triumphs, could not fully explain the workings of the atomic realm. A new paradigm was needed, one that embraced the bizarre and the counterintuitive. Through the groundbreaking work of pioneers like de Broglie, Schrödinger, and Heisenberg, the field of quantum mechanics took shape. It was a revolution every bit as profound as the discoveries of Copernicus or Newton, revealing a universe far stranger and more wondrous than anyone had dared to imagine. As the 20th century progressed, quantum mechanics would unleash a flood of new technologies and insights. From lasers and transistors to superconductors and magnetic resonance imaging, the fruits of the quantum revolution would transform daily life in ways that even the vaunted science fiction writers of the day could scarcely dream of. Yet even as scientists marveled at the progress unlocked by quantum theory, they found themselves grappling with unsettling philosophical implications. If a particle's properties depended on the act of measurement, what did that imply about the nature of reality itself? Did an electron exist in a coherent state before it was observed? Or did the very act of measurement call it into being? The famous thought experiment of Schrödinger's cat, forever suspended between life and death, playfully highlighted the apparent absurdities of the quantum world. Such questions would fuel spirited debates among the greatest minds in physics, from Bohr and Einstein to Heisenberg and Schrödinger. Even today, as quantum computers edge closer to reality and physicists probe the foundations of the subatomic world with ever more powerful particle accelerators, the deep mysteries posed by quantum theory continue to tantalize and inspire. The quantum revolution forever shattered the clockwork universe of Newton, replacing it with a cosmos where uncertainty reigned, and mind-boggling phenomena like quantum entanglement and wave-particle duality hinted at a deeper, more mysterious layer of reality. It was a humbling reminder of how much we still had to learn about the universe we inhabit. As the golden age of quantum mechanics unfolded through the early 20th century, other scientists were directing their gaze to the heavens, armed with powerful new telescopes and an insatiable curiosity about the cosmos. They too would soon make startling discoveries that would once again transform our understanding of the universe and our place within it. In the 1920s, American astronomer Edwin Hubble began training the world's largest telescope, the 100-inch Hooker reflector at Mount Wilson Observatory, on distant patches of sky. As he collected long-exposure photographs of faint, fuzzy objects then known as spiral nebulae, Hubble noticed something odd. Within these spirals he could discern individual stars, many of which appeared to be Cepheid variables, a special type of pulsating star whose intrinsic brightness could be inferred from the period of its pulsations. By comparing the apparent brightness of these Cepheids to their intrinsic luminosity, Hubble could estimate their distance, and what he found was staggering. The Cepheids, and by extension the spiral nebulae in which they resided, were far too distant to be part of our own Milky Way galaxy. Hubble had discovered that our galaxy was just one of countless island universes adrift in the vastness of space. It was a profound realization, one that suddenly made the cosmos seem unfathomably larger and more magnificent. The Milky Way, once assumed to be the full extent of the universe, was now just a speck amid a sea of galaxies stretching as far as the most powerful telescopes could see. Hubble had peered into the depths of space, and in the process, forever changed our cosmic perspective. But Hubble wasn't finished. As he continued to catalogue distant galaxies, measuring both their distances and the shift in the wavelength of their light, he noticed a curious pattern. The more distant a galaxy, the more its light was shifted towards the red end of the spectrum. It was as if the very space between us and these galaxies was stretching, like a cosmic fabric expanding in all directions. In 1929, Hubble and his assistant Milton Humason published their landmark paper describing this relationship between a galaxy's distance and its redshift. The implications were staggering. The universe itself appeared to be expanding, carrying galaxies along with it like raisins in a rising loaf of bread. The discovery of the expanding universe sent shockwaves through the scientific community. It was a finding that flew in the face of centuries of accepted wisdom about the cosmos. Since the time of Aristotle, astronomers had assumed the universe was eternal and unchanging. Now, in light of Hubble's work, that static picture had been shattered. If the universe was expanding, it must have been smaller in the past. Extrapolating backwards in time, it seemed the entire cosmos must have originated from an unimaginably dense and hot state, an idea that would come to be known as the Big Bang Theory. The notion of a universe with a beginning, born in a cosmic fireball billions of years ago, was nothing short of revolutionary. It completely upended humanity's understanding of our place in the grand sweep of time and space. No longer could we conceive of ourselves as inhabiting an eternal, unchanging cosmos. We now knew that the universe had a history, that it had evolved and transformed over immense spans of time to give rise to the majesty we see around us today. As the 20th century progressed, the Big Bang theory would find ever stronger support from astronomical observations. In 1948, physicists Ralph Alpher and George Gamow predicted that the intense heat of the early universe should have left behind a faint afterglow of microwave radiation permeating all of space, a fossil imprint of the Big Bang. That afterglow was accidentally discovered in 1964 by Arno Penzias and Robert Wilson of Bell Labs, who had been puzzling over a persistent background hiss in their radio antenna. The signal was the same in all directions, leading them to conclude it was coming from beyond our galaxy. In fact, it was the cosmic microwave background radiation predicted by Alpha and Gamow, a ghost of the Big Bang still whispering to us across billions of years. The discovery of the cosmic microwave background was a stunning confirmation of the Big Bang theory, cementing its place as the leading model of cosmic origins. As more precise measurements of this primordial light were made in the following decades, cosmologists could begin to piece together a detailed history of the early universe, tracing its fiery expansion and gradual cooling. At the same time, physicists were developing the theoretical tools needed to push our understanding even further back in time, to the very brink of the Big Bang itself. Theories of cosmic inflation, first proposed by Alan Guth in 1980, held that the universe had undergone a brief period of exponential expansion in its earliest moments, driven by the immense repulsive gravity of an exotic form of energy. Inflation provided an elegant explanation for several puzzling features of the cosmos, such as its remarkable large-scale uniformity and flatness. It also made predictions about the nature of the cosmic microwave background that would be spectacularly verified by high-precision satellite observations in the early 2000s. Yet even as inflation pushed our cosmic history back to within a fraction of a second of the Big Bang, the true origin of the universe remained shrouded in mystery. What had triggered inflation? What had existed before that initial expansion? Indeed, did our notions of before even have meaning in the extreme environment of the Big Bang? Physicists and cosmologists grappled with these profound questions as the 20th century gave way to the 21st. New ideas emerged, from eternal inflation and the multiverse to string theory and quantum gravity, each offering tantalizing glimpses of what might have preceded our observable universe. Yet definitive answers remained elusive, as the physics of the Big Bang pushed the boundaries of human knowledge to its very limits. As we ponder these deepest mysteries of existence, it's humbling to consider just how far cosmology has come since the days of Hubble and Gamow. In less than a century, we've gone from a static, eternal universe to a dynamic cosmos with a definite beginning, a rich history, and a vast future still unfolding. We've peered back in time to witness the birth of the first stars and galaxies, mapped the grand cosmic web that binds them together, and detected the ripples in space-time from colliding black holes more than 1 billion light-years away. Yet for all these incredible advances, we've only just begun to scratch the surface of the cosmos. As we continue to probe the universe with ever more sensitive telescopes and detectors, as we refine our theories and push them to new frontiers, there's no telling what remarkable surprises and revelations wait us. Perhaps we'll find evidence of extra dimensions curled up at the smallest scales, as predicted by string theory. Maybe we'll detect the telltale signature of other universes bumping up against our own, hinting at a vaster multiverse beyond our cosmic horizon. We might even discover that our universe is but one of infinitely many, each with its own unique physical laws and constants, in an eternal cycle of cosmic creation and destruction. These are the kinds of ideas that fire the imagination and fuel the sense of wonder that has always been at the heart of humanity's quest to understand the cosmos. From the first stargazers of antiquity to the cosmologists and astronomers of today, we've been driven by a profound desire to comprehend our place in the grand scheme of things, to glimpse the hidden workings of nature and revel in its beauty and mystery. So as we lay our heads down to rest, let us dream of the boundless possibilities that await us in the vast and majestic universe we call home. For even as we sleep, the great cosmic dance continues. Stars are born and die, galaxies collide and merge, and the very fabric of space-time ripples with the echoes of distant cataclysms. And somewhere out there, on a small blue planet orbiting an unremarkable star, a curious species looks to the night sky and wonders, marvelling at the grandeur of it all and daring to imagine what wonders the universe might yet hold. In that innate curiosity, that ceaseless quest for knowledge and understanding, lies the true beauty and power of the human spirit. So let us embrace that spirit, nurture it, and carry it forward as we continue to explore the mysteries of the cosmos. For in the end, the story of the universe is our story, written in starlight and etched in the hearts of all who have ever gazed up at the night sky in wonder. As we gently drift off to sleep, let us hold fast to that sense of wonder, secure in the knowledge that the universe still holds endless secrets waiting to be unveiled. And perhaps, in the quiet moments before dreams take hold, we might spare a thought for the countless generations of scientists and thinkers who have brought us to this point, who have illuminated the workings of nature and given us a glimpse of the awe-inspiring cosmos we inhabit. From Copernicus and Galileo to Newton and Einstein, from Hubble and Heisenberg to Hawking and Guth, these brilliant minds have been the torchbearers of our species' unending quest for understanding. Their insights and discoveries have not only reshaped our view of the universe, but have fundamentally altered the course of human history. Yet for all their individual genius, these scientists were also part of a larger tapestry, a grand and ongoing conversation that spans centuries and crosses cultures. Every breakthrough, every eureka moment was built on the foundation of countless hours of study, experimentation, and debate, often undertaken by unsung heroes whose names have been lost to history. It's a reminder that science is, at its core, a profoundly human endeavour, a collective enterprise that transcends any one individual or nation. It's a testament to the power of curiosity, creativity, and perseverance in the face of nature's deepest enigmas. And it's an invitation to each and every one of us to take part in this grand adventure, to add our own voices to the great cosmic conversation, whether as professional scientists or amateur enthusiasts, as teachers or students, as parents or children filled with wonder. We all have a role to play in the ongoing quest to unravel the mysteries of the universe. So as we slip softly into the realm of dreams, let us carry with us a renewed sense of our place in the cosmic story. Let us marvel at the incredible journey of discovery that has brought us to this moment, and let us look forward with hope and excitement to the many wonders that surely lie ahead. For as long as there are stars in the sky and curious minds to ponder them, the great saga of science will continue to unfold, forever pushing the boundaries of our knowledge and reaffirming our sense of wonder at the magnificent universe we call home. And with that uplifting thought, let us bid a fond goodnight to the cosmos, secure in the knowledge that the journey of discovery will be waiting for us when we awake. May your dreams be filled with the beauty and mystery of the universe, and may the spirit of curiosity guide you always. Good night, and pleasant dreams. As we unravelled the secrets of the elements, the same era saw brilliant minds grapple with another profound mystery, the perplexing nature and behaviour of light itself. For centuries, scientists had debated whether light was composed of particles or waves, but in 1701, a pivotal experiment by English polymath Thomas Young would shed new light, if you'll pardon the pun, on this age-old question. Born in 1773 to a Quaker family in Somerset, England, Young was a precocious child who taught himself to read by the age of 2. A true polymath in the mould of Leonardo da Vinci, Young's insatiable curiosity spanned languages, medicine, Egyptology, music, and physics. But it was his famous double-slit experiment in 1801 that would etch his name in the annals of science history. In a darkened room, Young cut 2 narrow parallel slits in a screen and shone a beam of light through them onto a second screen. To his astonishment, instead of 2 bright lines appearing on the back screen as expected for light particles, Young observed a pattern of alternating light and dark bands. This striped pattern, he realised, could only be explained if light was behaving as a wave, with crests and troughs from each slit interfering to create the bands. The double-slit experiment was a revelation, providing the first clear evidence of light's wave-like nature. Despite Young's experimental coup, the particle versus wave debate would rage on well into the 20th century. In 1900, German physicist Max Planck inadvertently planted the seeds for a quantum revolution while grappling with another mystery of light, the so-called ultraviolet catastrophe. Classical physics predicted that hot objects should emit infinite amounts of ultraviolet radiation, yet this clearly contradicted real-world observations. Planck made a bold assumption that light could only be emitted or absorbed in discrete packets he called quanta. Like turning a dimmer switch in steps rather than a smooth gradient, energy could only change in set amounts determined by a constant, which we now know as Planck's constant. By quantizing energy, Planck resolved the ultraviolet catastrophe and laid the groundwork for quantum mechanics, a revolutionary new framework for physics at the smaller scales. But it was Planck's contemporary, a young patent clerk named Albert Einstein, who would take the quantum idea and run with it. In 1905, Einstein had his Annus Mirabilis, or Miracle Year, publishing a flurry of papers that would shake the foundations of physics. Among them was his groundbreaking work on the photoelectric effect, the observation that certain metals emit electrons when struck by light. Einstein boldly suggested that light was composed of discrete particles he called photons, with each photon's energy determined by its frequency. This was a radical break from the classical wave theory of light, but Einstein's equations elegantly explained the photoelectric effect. Despite initial skepticism, Einstein's theory was vindicated by experiments and earned him the Nobel Prize in 1921, enshrining the photon as a fundamental particle in quantum mechanics as a pillar of modern physics. Among Einstein's other Miracle Year papers were his special theory of relativity, which unified space and time and revealed the speed of light as the cosmic speed limit, and his famous equation E equals mc squared, which revealed the equivalence of mass and energy. Together, relativity and quantum mechanics would form the twin foundations of 20th century physics, their strange and counterintuitive predictions repeatedly verified by ever more precise experiments. Yet even as Einstein ushered in the quantum age, he grew increasingly uncomfortable with the theory's probabilistic nature and apparent paradoxes. God does not play dice with the universe, Einstein famously quipped in a letter to Max Born in 1926. But a new generation of physicists were eagerly playing with quantum dice and repeatedly rolling scientific sixes. In 1924, French aristocrat and physicist Louis de Broglie proposed a bold idea. If light could behave like particles as Einstein had shown, could particles also behave like waves? Applying Planck's constant, de Broglie calculated a wavelength for electrons and suggested that all matter, not just light, should exhibit wave-like properties at the quantum scale. Experiments soon confirmed de Broglie's hypothesis, detecting diffraction patterns from beams of electrons analogous to those of light waves. Austrian physicist Erwin Schrödinger took the matter wave idea and ran with it. In 1926, Schrödinger published his famous wave equation, which became the mathematical foundation of quantum mechanics. The Schrödinger equation describes the wave-like behavior of particles using a wave function, with the particle's position and momentum encoded as probabilities rather than definite values. Schrödinger's equation yielded many strange predictions, such as a particle being in two places at once, or even in two different energy states simultaneously. But perhaps the equation's most famous consequence was Schrödinger's cat, a thought experiment highlighting the bizarre implications of quantum superposition. Imagine, Schrödinger proposed, a cat sealed in a box with a vial of poison and a radioactive source. If a single atom of the source decays, a mechanism breaks the vial, killing the cat. In the weird world of quantum mechanics, the radioactive atom exists in a superposition of decayed and undecayed states until it is observed. By extension, is the cat alive, dead, or somehow both until we open the box? While animal lovers can rest assured no actual felines were harmed in the making of this thought experiment, Schrödinger's cat vividly demonstrated how the quantum world defies our everyday intuitions. A particle, like the cat, seemingly exists in multiple contradictory states at once, collapsing to a definite state only when measured. Einstein and others railed against this apparent paradox, believing quantum theory was incomplete. But as experiments probed the subatomic realm with ever greater precision, quantum mechanics continued to pass every test with flying colours. Schrödinger was not the only pioneer of quantum mechanics in the 1920s. German physicist Werner Heisenberg developed his own mathematical formulation based on matrices, which proved equivalent to Schrödinger's wave mechanics. But Heisenberg's most famous contribution was his uncertainty principle, which he introduced in 1927. The uncertainty principle states that the more precisely you measure a particle's position, the less precisely you can know its momentum and vice versa. This is not a limitation of our measuring devices, but a fundamental property of the quantum world. Like a blurry photograph, the act of observing a particle unavoidably disrupts it, with the trade-off between position and momentum precision built into the fabric of reality. Together, the Schrödinger equation and Heisenberg's uncertainty principle form the bedrock of quantum mechanics. Over the next decades, physicists would apply this powerful framework to illuminate the inner workings of atoms, the behavior of materials, the nature of chemical bonds, and the evolution of stars. Quantum theory became one of the most successful and well-tested theories in all of science, unlocking the secrets of semiconductors, lasers, superconductors, and myriad other technologies that shape our modern world. Yet even as quantum mechanics matured and found practical application, its philosophical implications continued to unsettle and captivate. Einstein spent his later years doggedly pursuing a unified field theory that would reconcile gravity with electromagnetism and banish the disturbing paradoxes of the quantum realm. While Einstein's quest would prove quixotic, his iconic status lent the mysteries of quantum mechanics a cultural cachet that endures to this day. Even now, a century after Bohr, Schrödinger, and Heisenberg laid the foundations of quantum theory, physicists and philosophers still grapple with interpreting its bizarre yet undeniable consequences. From Schrödinger's cat to quantum entanglement to the many worlds interpretation, quantum concepts continue to capture the public imagination and inspire mind-bending thought experiments. One can only wonder what Planck and Einstein would make of the quantum world they unwittingly discovered. With each new experimental confirmation, from the detection of the Higgs boson to the entanglement of ever larger objects, quantum mechanics only seems to grow more inescapably strange and more inescapably true. Like an endless fractal or an Escher staircase, the quantum realm invites us to reshape our intuitions and expand our sense of the possible. As we come to the end of our tour through the Masters of Light, it's fitting to pause and marvel at how far our understanding has come since Thomas Young first glimpsed light's wave-like nature 2 centuries ago. From the photoelectric effect to the uncertainty principle, the quantum revolution has illuminated the fundamental building blocks of nature in all their strange and shimmering glory. And yet, as we'll see, the cosmic dance of light and matter extends far beyond the subatomic realm to the largest scales imaginable. For even as physicists were decoding the quantum mysteries of the small, a new generation of astronomers was training telescopes on the heavens and uncovering breathtaking vistas of the mind-bogglingly big. But those cosmic revelations will have to wait for another time. For now, as your mind gently turns over the remarkable discoveries we've explored, from the elements to the atoms to the enigmas of light, know that your dreams will drift through a universe both stranger and more wonderful than those brilliant minds of centuries past could have ever imagined. The soft darkness beyond your closed eyes is shot through with the shimmering quantum dance of photons and electrons, a ceaseless symphony of energy and matter playing out on the Planck scale. Each breath you take is an exchange of atoms first forged in the hearts of stars, a whisper of cosmic history, eons in the making. So rest now, and let your dreams wander along the path of wonders we've traced from a candle flame dancing on an ancient Greek shore, to the subatomic realms where matter and light blur and reality itself grows fuzzy at the edges. The journey of science is a journey without end, for each answer only uncovers new questions inviting further exploration. And if, as you drift off, you find yourself smiling at a particularly clever pun, or marvelling at the sheer improbability of a universe so grand and yet so knowable, then I'll count this humble account of science history a lullaby well sung. For in the end, what sweeter dreams could we ask for than those of an ever-expanding understanding and an ever-deepening appreciation for the magnificent, mysterious cosmos we call home? Good night, dear listener, and may your dreams be as vast and full of wonder as the universe itself. The name most associated with the early days of the electrical age is Benjamin Franklin. In June 1752, Franklin conducted his famous kite experiment, an almost foolhardy investigation driven by his fascination with electricity. As a thunderstorm raged over Philadelphia, Franklin ventured out with his son William. They attached a metal key to a silk kite and sent it soaring. As the kite danced perilously among the storm clouds, Franklin felt the fibres of the kite string stand on end, a clear sign they were conducting an electric charge from the lightning overhead. When Franklin brought his knuckle close to the key, a spark jumped the gap, delivering an electric shock and vindicating his hypothesis. With this daring experiment, Franklin had proved that lightning was an electrical phenomenon. It was a watershed moment. By showing that electricity existed in nature, and not just in the laboratory, Franklin ushered in a new paradigm where experimenters began seeking to harness and utilize this primal force of nature for human benefit. The seed was planted for an electrical revolution that would transform civilization in the coming centuries. In 1800, the Italian physicist Alessandro Volta invented the first true battery, the voltaic pile. Volta's battery consisted of alternating discs of zinc and copper separated by brine-soaked cloth or cardboard. When the top and bottom of the pile were connected by a wire, an electric current flowed continuously for a substantial length of time. Volta's invention was groundbreaking. Previously, scientists could only produce static charges that dissipated almost instantly. But the voltaic pile provided a steady, lasting current that could power electrical devices. It became an essential laboratory tool, allowing far more sophisticated experiments than ever before. More importantly, Volta had shown it was possible to store electrical energy and deliver it on demand, the foundational concept of every battery in use today. The early 1800s saw a flourishing of electrical research as scientists raced to explain the mechanisms behind Volta's battery and push the boundaries of what was possible. In 1820, the Danish physicist Hans Christian Ørsted made a discovery that would once again revolutionize our understanding of electricity's role in the universe. During a lecture demonstration, Ørsted noticed that whenever an electric current from a battery was switched on or off, a nearby compass needle would twitch. Intrigued, he soon determined that an electric current produces a circular magnetic field around it. Electricity and magnetism, long thought to be separate forces, were intimately linked. Ørsted's finding sent shockwaves through the scientific community and inspired a new generation of electricians, as they were then known, to explore electromagnetism. Suddenly, electricity was not just a curious effect to be studied in the lab, but a force that could exert mechanical action at a distance, just like gravity. The implications were profound for science and for technology. The most prolific of these new electrical researchers was Michael Faraday. From his lab at the Royal Institution in London, Faraday would conduct the experiments that laid the foundation for our modern, electrified world. His great breakthrough came in 1831 with the discovery of electromagnetic induction, the principle behind the electric generator and transformer. Faraday found that moving a magnet through a coil of wire caused an electric current to flow in the wire. Conversely, passing a current through a wire would cause a stationary magnet to move, the basis for the electric motor. These twin discoveries revealed that electricity and magnetism were two sides of the same coin, interconvertible forms of energy. With this unifying insight, Faraday had discovered a fundamental law of the universe and ushered in a second industrial revolution. Electric generators would allow easy and efficient production of this versatile form of energy on a mass scale. Electric motors would find their way into everything from locomotives to household appliances. Our modern electrified world, with power available at the flip of a switch, can be traced directly back to Faraday's coils of wire and inquisitive mind. The next leap forward in our understanding of electromagnetism came from the brilliant Scottish physicist James Clerk Maxwell. In 1865, Maxwell published his masterwork, a set of equations that unified everything that was then known about electricity and magnetism into one elegant mathematical framework. Maxwell's equations showed that electric and magnetic fields travel through space as waves moving at the speed of light. In fact, Maxwell concluded that light itself was just one portion of a broad spectrum of possible electromagnetic waves, differing only in their wavelength. With this stunning insight, Maxwell had shown that electricity, magnetism, and light were all manifestations of the same phenomenon, the electromagnetic force. It was one of the great unifying moments in physics, explaining seemingly disparate concepts within one overarching theory. 100 years before, Franklin had shown that lightning was electrical in nature. Now, Maxwell had gone one step further and shown that light was too. Maxwell's theory also predicted the existence of a vast array of electromagnetic waves beyond the narrow band of visible light, including radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. He had introduced the concept of the electromagnetic spectrum. It would take a few decades for experimental confirmation of Maxwell's electromagnetic waves, but he had shown the way. In subsequent years, physicists would discover and harness each of these wave bands, enabling technologies like radio, television, radar, X-ray imaging, and radio astronomy that shape our modern world. The journey from Franklin's kite to Maxwell's equations is one of the great arcs of scientific discovery, a series of inspired insights that transformed our view of nature and unlocked a new era of human capability. As the 1800s drew to a close, the mystery of electricity had largely been tamed. But at the same time, new puzzles were emerging in chemistry as scientists sought to understand the properties and behaviour of matter at its most fundamental level. The quest to unravel the elements soon kicked into high gear. The 19th century was a golden age of chemistry, as researchers raced to fill out the periodic table with new discoveries. In 1869, the Russian chemist Dmitry Mendeleev published his first periodic table, arranging the elements in rows and columns by their atomic weight. Mendeleev's great insight was to recognize repeating patterns in the properties of the elements, and to leave gaps where he predicted new elements would later be found. The predictive power of the periodic table was a clear sign that some deeper order lay behind the array of chemical substances. But what was the underlying structure of the atom that gave rise to these patterns? It would take a new generation of physicists in the early 20th century to unravel this mystery. One of the leading figures in this new atomic science was Marie Curie. Curie was a true scientific pioneer, not only in her groundbreaking discoveries, but in her very identity as a woman in a male-dominated field. Born Maria Skłodowska in Warsaw in 1867, Curie later moved to Paris, where she became the first woman to teach at the Sorbonne. In 1896, Curie began investigating the strange phenomenon of uranium rays, which had recently been discovered by Henri Becquerel. Through meticulous chemical separation experiments, Curie managed to isolate two new elements that were even more radioactive than uranium, polonium and radium. For this landmark discovery, Curie coined the term radioactivity. Her painstaking research revealed that radioactivity was an atomic property, some fundamental process taking place inside the atoms of certain elements. Curie had shown that the atom was not indivisible after all, but contained substructure and internal forces. It was the first glimpse behind the veil of atomic physics. Curie's research also highlighted the potential of radioactivity for biomedical applications. Radiation from radium, it was found, could destroy tumour cells, leading to some of the first successful cancer treatments. But this medical advance came at great personal cost. Curie herself would later succumb to leukemia caused by radiation exposure, a tragic end for one of history's most brilliant scientists. At the dawn of the 20th century, a New Zealand-born physicist named Ernest Rutherford picked up where Curie left off. Through a series of scattering experiments, Rutherford probed the inner structure of the atom and discovered that its mass was entirely concentrated in a tiny, dense nucleus at the centre. The rest of the atom was mostly empty space. This nuclear model of the atom marked a radical break from earlier plum pudding theories that envisioned a diffuse cloud of positive charge. Rutherford had shown that the atom was built like a miniature solar system, with lightweight electrons orbiting a dense nucleus. His discovery laid the groundwork for all of nuclear physics and chemistry to come. The next breakthrough in atomic theory came from the Danish physicist Niels Bohr. Bohr proposed that electrons orbit the nucleus in fixed shells, and that they can jump between these quantized orbits by emitting or absorbing packets of electromagnetic energy, quanta of light. Bohr's quantum model resolved many of the puzzling features of atomic spectra and chemical bonding that had confounded scientists for decades. At the same time, it introduced a strange new subatomic world where the crisp certainty of Newtonian physics gave way to probabilistic quantum rules. The quantum revolution had begun. In subsequent decades, physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac would develop the full mathematical framework of quantum mechanics, one of the most successful scientific theories of all time. Their work revealed the fundamental wave-particle duality of matter and energy, the strange phenomenon of quantum entanglement, and the inherent uncertainty woven into the fabric of the universe at the smallest scales. As the 20th century progressed, physicists continued to probe the structure of matter at ever higher energies and smaller scales. In the 1960s, Murray Gell-Mann and George Zweig independently proposed that protons and neutrons were composed of even more fundamental particles called quarks. Later experiments confirmed that the atomic nucleus was a seething cauldron of quarks and gluons, bound together by the strong nuclear force. By the end of the 20th century, physicists had painted a remarkably complete picture of the subatomic world known as the Standard Model. From the chemical elements of Mendeleev's periodic table down to the fundamental quarks and leptons, the basic building blocks of matter had been discovered and arranged into an elegant theoretical framework. But even as we plumb the depths of the quantum realm, new horizons have opened up on the cosmic scale. In the early decades of the 20th century, our view of the universe would be forever changed by another pair of brilliant physicists and an expanding web of light stretching to the far reaches of space and time, to be continued, measuring the charge-to-mass ratio of cathode rays. Through a series of meticulously designed experiments, he demonstrated that these rays were actually streams of particles much smaller than atoms, with a negative electric charge. He initially called them corpuscles, but they would later become known as electrons, the first subatomic particle to be discovered. Thomson's revelation in 1897 that atoms were not the indivisible building blocks of matter as long assumed sent shock waves through the scientific community. It ignited a flurry of research into the inner workings of the atom in the early 20th century, leading to the development of quantum physics and launching the field of particle physics. For his pioneering work, Thomson was awarded the Nobel Prize in Physics in 1906, but Thomson's model of the atom, a plum pudding with electrons embedded in a positively charged substrate, would not stand for long. In 1909, Ernest Rutherford, who had studied under Thomson, conducted a now famous experiment that would reshape our understanding of atomic structure. Along with his colleagues Hans Geiger and Ernest Marsden, Rutherford fired a beam of alpha particles at a thin gold foil, expecting them to pass straight through. To their astonishment, a small fraction of the particles bounced back. This unexpected result led Rutherford to propose a new model of the atom in 1911. In stark contrast to Thomson's plum pudding, Rutherford's atom had a tiny, dense, positively charged nucleus surrounded by electrons, an arrangement he compared to a miniature solar system. This landmark discovery marked the birth of nuclear physics. Rutherford later became the first person to split the atom and the first to transmute one element into another. He received the Nobel Prize in Chemistry in 1908 for his investigations into radioactive decay. Rutherford's model of the nuclear atom paved the way for the next great leap in physics, the quantum revolution. As the 20th century dawned, classical physics appeared to be a complete and well-tested framework explaining the natural world. The theories of Isaac Newton in mechanics and James Clerk Maxwell in electromagnetism seemed to describe the universe like perfectly meshed gears in a grand cosmic clockwork. But a few pesky anomalies hinted at cracks in the facade. The orbit of Mercury didn't quite match Newton's equations. The curious behaviour of light in certain situations defied classical expectations, and the glow from hot objects failed to align with established theories, an issue known as the ultraviolet catastrophe. In the early 1900s, a generation of young physicists began to question the assumptions of classical physics, embarking on a bold voyage into the uncharted waters of the atomic realm. Their daring explorations would topple the clockwork universe, replacing it with an otherworldly reality governed by probabilistic weirdness and infused with inescapable uncertainty. At the forefront of this quantum vanguard stood an unlikely revolutionary, a modest German scientist with a penchant for late-night violin concertos. His name was Max Planck, and in 1900 he would plant the seed that grew into quantum theory. While grappling with the ultraviolet catastrophe, the prediction by classical theories that a hot object should emit infinite power at high frequencies, Planck made a bold assumption. He proposed that atoms could only emit or absorb energy in discrete packets, which he called quanta. Like a cosmic vending machine that only accepts exact change, Planck's quantized energy could only come in multiples of a fundamental constant, which became known as Planck's constant. Planck viewed his energy quanta as a mathematical trick to get the theory to match experimental results. He spent years trying to reconcile it with classical physics, but the ultraviolet catastrophe was averted and the equation worked, a bit too well. Try as he might, Planck couldn't unring the quantum bell. What began as a mathematical sleight of hand would soon upend the foundations of physics. 5 years later, Planck's notion of quantized energy would find an ardent champion in a brilliant young patent clerk dreaming of riding alongside a light beam. Albert Einstein took Planck's quanta and ran with them, applying the concept to light itself. In his groundbreaking 1905 paper explaining the photoelectric effect, Einstein proposed that light travels through space not as a continuous wave, but as a stream of discrete energy packets, tiny bundles he called photons. Einstein's photons handily explained the photoelectric effect, but they flew in the face of centuries of research into the wave nature of light. It was sacrilege, suggesting that the venerable theory of electromagnetism was incomplete. Many physicists scoffed, but Einstein would be vindicated in 1923 when Arthur Compton observed photons colliding with electrons, proving light's particle nature once and for all. For his services to theoretical physics, Einstein received the Nobel Prize in 1921, not for relativity, but for the photoelectric effect. The quantum genie was out of the bottle. The budding quantum theory continued to rack up successes throughout the early decades of the 20th century, as physicists deployed it to tackle a widening array of atomic phenomena. In 1913, Niels Bohr proposed a quantum model of the atom with electrons orbiting the nucleus in discrete energy shells, a planetary model that refined Rutherford's miniature solar system. Bohr's model explained the bright line spectra emitted by different elements, which appear when electrons hop between orbits. In 1924, French aristocrat Louis de Broglie further blurred the wave-particle distinction, proposing that just as light has particle-like properties, matter has wave-like properties. According to de Broglie, every particle, whether a photon, electron or atom, is associated with a wavelength inversely proportional to its momentum. At macroscopic scales, these matter waves are vanishingly small, but in the subatomic realm they can't be ignored. Experiments soon confirmed de Broglie's hypothesis, detecting electron waves diffracting through crystals. Austrian physicist Erwin Schrödinger built on de Broglie's concept, crafting a wave equation in 1926 that became the mathematical heart of quantum mechanics. Schrödinger envisioned electrons not as particles orbiting the nucleus, but as standing waves, ripples of probability surrounding the atom. These orbitals come in a variety of shapes, from simple spheres to complex lobed structures. Schrödinger's equation, which describes how these matter waves evolve over time, is a pillar of modern quantum theory. But it was Werner Heisenberg who, in 1927, codified the inner workings of the quantum realm with his famous uncertainty principle. According to Heisenberg, it's impossible to simultaneously know a particle's exact position and momentum. The more precisely you measure one, the more uncertain the other becomes. This isn't a limitation of our measuring tools, but a fundamental feature of reality at the quantum scale. It implies that subatomic particles don't have definite positions and velocities, but instead exist in a haze of probability until observed. The uncertainty principle, along with the waviness of matter, lies at the heart of quantum weirdness. It's why electrons can tunnel through barriers and why the quantum world is inherently unpredictable. Heisenberg's insight was a profound break from the deterministic gears of classical physics, where the present state of a system completely determines its future. In the quantum realm, the future is probabilistic, a roll of the dice with the odds determined by Schrödinger's equation. Throughout the late 1920s and 1930s, the titans of the quantum revolution continued to refine and extend the theory, grappling with its often counterintuitive implications. Paul Dirac combined quantum mechanics with special relativity in 1928, devising an equation that implied the existence of antimatter, a prediction confirmed in 1932 with the discovery of the positron. Dirac, along with Heisenberg and Schrödinger, shared the 1933 Nobel Prize in Physics for their contributions to quantum theory. Other quantum pioneers explored the philosophical implications of this strange new worldview. Bohr developed the Copenhagen interpretation, which holds that a quantum system doesn't have definite properties until it's measured, a concept he called complementarity. Bohr's protégé, John von Neumann, formalized the mathematical structure of quantum mechanics in the 1930s, introducing concepts like Hilbert spaces and density matrices. But perhaps the most famous thought experiment in quantum mechanics came from Schrödinger himself. In 1935, as a critique of the Copenhagen interpretation, Schrödinger proposed a scenario involving a cat in a box with a vial of poison and a radioactive source. If an atom of the source decays, it triggers the poison, killing the cat. But in the strange world of quantum mechanics, the cat exists in a superposition of alive and dead states until an observer opens the box and collapses the wave function. Schrödinger's cat, while never intended as a serious model, highlights the apparent absurdity of applying quantum laws to everyday objects. It cuts to the heart of the measurement problem in quantum mechanics, the still unresolved question of how the act of observation collapses a system's wave function, forcing it to choose a definite state. Decades later, the unfortunate feline remains a cultural touchstone, a reminder of the deep puzzles posed by the quantum world. As the 20th century progressed, quantum mechanics proved to be one of the most successful scientific theories ever devised. It underlies our understanding of atoms, molecules, and the fundamental particles that make up the universe. Its mathematical framework is essential for designing lasers, transistors, and the other building blocks of modern electronics. Quantum theory enables MRI machines to peer inside the human body and scanning tunneling microscopes to image individual atoms. It's the basis for emerging technologies like quantum computers, quantum cryptography, and quantum sensors. Yet for all its triumphs, quantum mechanics remains deeply perplexing, with implications that challenge our intuitive grasp of reality. Its weirdness has inspired countless philosophical debates and pop culture references, from the many worlds interpretation to quantum mysticism. As physicist Richard Feynman famously quipped, "If you think you understand quantum mechanics, you don't understand quantum mechanics." A century after its birth in the mind of Max Planck, quantum theory continues to be a vibrant field of research, with new experimental tests and theoretical extensions pushing the boundaries of our knowledge. From quantum entanglement to quantum gravity, the quest to fathom the subatomic world remains one of the great scientific adventures of our time. The quantum realm, once dismissed as a mathematical curiosity, has proven to be the bedrock of reality. A looking-glass world where waves are particles, particles are waves, and nothing is quite what it seems. As our journey through the history of science continues, we leave behind the surreal landscape of the quantum and ascend to the cosmic scale. In the early decades of the 20th century, while Bohr and Heisenberg were peering into the heart of the atom, another revolution was brewing, one that would reshape our understanding of space, time, and gravity. Its architect was a young patent clerk who, in 1905, unleashed a flurry of papers that rocked the foundations of physics. His name was Albert Einstein, and his special theory of relativity would set the stage for a new conception of the universe. Before Einstein, space and time were seen as absolute and independent, an immutable stage on which the drama of physics unfolded. But Einstein realized that the speed of light, as measured by all observers, is constant regardless of their motion. This simple fact has mind-bending consequences. It means that moving clocks tick more slowly than stationary ones, a phenomenon called time dilation. It means that objects contract along their direction of motion, an effect known as length contraction. And it means that simultaneity is relative. Events that occur at the same time for one observer might happen at different times for another. These counterintuitive effects, while negligible at everyday speeds, become significant as one approaches the speed of light. They imply that space and time are not absolute, but are instead intertwined aspects of a four-dimensional space-time continuum. The passage of time and the measurement of distance depend on the relative motion of the observer. Space and time, once thought to be the unchanging stage of the cosmos, are revealed to be malleable and dynamic participants in the dance of reality. Einstein didn't stop there. In a second paper published later in 1905, he derived the most famous equation in history, E equals mc squared. This deceptively simple formula encodes one of the deepest truths about the universe. Energy and mass are equivalent and interchangeable. The energy contained in a massum is equal to that mass multiplied by the speed of light squared. A small amount of matter, if converted entirely to energy, could power a city. The sun shines by slowly converting a fraction of its immense mass into radiant energy. E equals mc squared underlies the awesome power of nuclear reactions, from the fusion that fuels the stars to the fission that drives atomic bombs. Special relativity was a stunning intellectual achievement, but it was only a prelude to Einstein's true masterpiece. After a decade of intense thought, in 1915 he unveiled the general theory of relativity, a radical reimagining of gravity not as a force, but as the curvature of space-time itself. In Einstein's universe, massive objects warp the fabric of space-time, creating the illusion of gravitational attraction. Freely falling objects simply follow the straightest possible paths in curved space-time, like balls rolling on a stretched rubber sheet. General relativity makes a host of startling predictions. It explains the precession of Mercury's orbit, which Newton's theory couldn't fully account for. It predicts that light rays will bend around massive objects, an effect dramatically confirmed during a solar eclipse in 1919. It implies that gravity can slow down time, a fact that must be accounted for in GPS satellites. And perhaps most remarkably, it allows for the existence of black holes, singularities in space-time where gravity becomes so intense that not even light can escape. Einstein's theory also opened the door to a new understanding of the universe as a whole. In 1917, Einstein applied general relativity to the entire cosmos, introducing the idea of a static universe that was infinite in both space and time. But this model required an additional term in his equations, the infamous cosmological constant, to counteract the pull of gravity and keep the universe from collapsing. When Edwin Hubble discovered in 1929 that distant galaxies are receding from us, evidence that the universe is in fact expanding, Einstein abandoned the cosmological constant, calling it his greatest blunder. The expanding universe, along with general relativity, led to the development of the Big Bang theory by Georges Lemaitre and others in the 1930s. According to this model, the universe began in an incredibly hot, dense state, around 13.8 billion years ago, and has been expanding and cooling ever since. The discovery of the cosmic microwave background radiation in 1964, an afterglow of the primordial fireball predicted by the theory, was a major triumph for the Big Bang model. General relativity has withstood a century of experimental tests, from the bending of starlight to the slowing of atomic clocks in Earth's gravitational field. Its predictions were spectacularly confirmed in 2015 with the first direct detection of gravitational waves, ripples in space-time caused by cataclysmic events like colliding black holes. The Laser Interferometer, Gravitational Wave Observatory, LIGO, measured these minuscule distortions in space-time, ushering in a new era of astronomy. Yet for all its successes, general relativity leaves some deep questions unanswered. It breaks down at the centre of black holes and at the moment of the Big Bang, where the math predicts nonsensical infinities. Attempts to reconcile general relativity with quantum mechanics, to unify gravity with the other forces of nature, remain one of the great unsolved problems in physics. Candidates like string theory and loop quantum gravity offer tantalizing hints, but a true quantum theory of gravity remains elusive. As we ponder these cosmic conundrums, our journey through the history of science draws to a close. From the celestial spheres of Ptolemy to the warped space-time of Einstein, from the classical certainties of Newton to the quantum weirdness of Bohr and Heisenberg, we've traced the arc of human understanding as it reaches toward the deepest mysteries of the universe. Along the way, we've met a host of brilliant minds who dared to question the status quo, to venture beyond the boundaries of the known: Copernicus and Galileo, who upended the Earth-centered cosmos; Lavoisier and Dalton, who transformed chemistry from a hodgepodge of haphazard observations into a rigorous science; Darwin and Wallace, who revealed the ancient tree of life shaped by natural selection; Curie and Meitner, who pioneered the study of radioactivity and nuclear fission; Hubble and Lemaitre, who discovered the expanding universe and the echo of the Big Bang. These scientific titans and countless others remind us that the edifice of human knowledge is a collective construction, built brick by brick, insight by insight, over centuries of patient observation, bold theorizing and diligent experimentation. Every discovery, every conceptual leap is a triumph of the restless human drive to understand, to light a candle in the dark and push back the frontiers of the unknown. As we've seen, the path of science is rarely a straight line. It's paved with false starts and blind alleys, with ideas that once seemed unassailable, but are later discarded in the face of new evidence. Aristotelian physics, phlogiston theory, the luminiferous ether, these and other obsolete notions litter the history of science, relics of our imperfect and ever-evolving understanding. Yet this is the strength and the beauty of the scientific method. It is a self-correcting process, a continual refinement of our knowledge in the crucible of empirical testing. As we continue our journey through the most important scientific discoveries of all time, we come to a transformative era that fundamentally changed how we perceive and interact with the world around us, the age of electrifying discoveries. In the late 1700s, scientists began to shed light on one of nature's most captivating and mysterious phenomena, electricity and magnetism. The famous American polymath Benjamin Franklin was at the forefront of this electrical enlightenment. In a dangerous yet ingenious experiment, Franklin flew a kite with a metal key attached during a thunderstorm in 1752. When the key became charged and produced sparks, he had proven that lightning was indeed electrical in nature. Around the same time, French physicist Charles Coulomb was investigating the fundamental properties of electric charges. Through meticulous experiments with a torsion balance, Coulomb discovered in 1785 that the force between two electric charges is inversely proportional to the square of the distance between them. This became known as Coulomb's law, a cornerstone of electrostatics. The stage was now set for a rapid series of breakthroughs that would transform our understanding of electricity and magnetism. In 1799, Italian physicist Alessandro Volta invented the first electric battery, known as the Voltaic pile. By stacking alternating layers of copper and zinc separated by brine-soaked cloth, Volta created a steady flow of electric current. This invention ushered in a new age of electronics and paved the way for countless technological marvels to come. But the connection between electricity and magnetism remained shrouded in mystery until 1820, when Danish physicist Hans Christian Ørsted made a serendipitous discovery. While preparing for a lecture, Ørsted noticed that a compass needle was deflected when an electric current flowed through a nearby wire. He had stumbled upon a fundamental link between these two forces of nature. Ørsted's discovery paved the way for the development of electric motors and generators, which convert between electrical and mechanical energy. Building on Ørsted's work, English scientist Michael Faraday conducted pioneering research in electromagnetism during the 1830s and 1840s. Through a series of ingenious experiments, Faraday demonstrated that a changing magnetic field could induce an electric current in a conductor, a phenomenon known as electromagnetic induction. He also discovered that magnetic fields could affect light, an effect known as Faraday rotation. Faraday's groundbreaking insights laid the foundation for our modern understanding of electromagnetism. In 1865, Scottish physicist James Clerk Maxwell achieved a remarkable synthesis of the disparate laws and phenomena of electricity and magnetism. In a series of elegant mathematical equations, Maxwell unified the work of Coulomb, Ørsted, Faraday and others into a coherent theory of electromagnetism. Maxwell's equations showed that electric and magnetic fields could propagate through space as waves, travelling at the speed of light. In a stunning revelation, Maxwell realised that light itself was an electromagnetic wave. Electricity, magnetism and light were all interconnected manifestations of the same fundamental force. One can only imagine the sense of wonder and awe that scientists of the day felt as they slowly pieced together this intricate tapestry of nature. The abstract concepts of electric and magnetic fields, previously thought separate, were now understood to be intimately linked, and the ethereal phenomenon of light, once believed to be of an entirely different character, was now recognized as an electromagnetic wave dancing to the tune of Maxwell's equations. As we take a moment to marvel at these profound insights, our minds drift back to the brilliant individuals who illuminated the mysteries of the electromagnetic world. From Franklin and Coulomb's early experiments to Ørsted and Faraday's crucial discoveries to Maxwell's crowning theoretical achievement. Their collective efforts ushered in a new paradigm for understanding some of the most ubiquitous phenomena in the universe, laying the groundwork for the myriad electronic and photonic technologies that shape our modern world. But the story of scientific discovery was far from over. As we continue our journey, we'll see how the same curious and methodical approach that unlocked the secrets of electricity and magnetism would next be applied to unravelling the very building blocks of matter itself, the chemical elements. And so we find ourselves at the frontiers of modern science, marvelling at the revolutionary discoveries and insights that have emerged in recent decades. The standard model of particle physics, developed in the 1960s, has brought a new level of clarity to the subatomic realm, elegantly organising the zoo of particles into a periodic table of sorts. This powerful framework rests upon the concept of quarks, those curious building blocks of matter first proposed independently by physicists Murray Gell-Mann and George Zweig in 1964. For years, the Standard Model remained incomplete, awaiting the detection of a keystone particle, the Higgs boson. Theorized in the 1960s by Peter Higgs and others, this elusive entity was predicted to endow other particles with mass via interactions with the all-pervading Higgs field. After a decades-long hunt and the construction of the world's most powerful particle accelerator, the Large Hadron Collider, the Higgs boson was at last discovered in 2012, cementing the foundations of particle physics and opening new avenues of inquiry. Meanwhile, astrophysicists have been chasing phantoms of another sort, gravitational waves, those ripples in the fabric of space-time first envisioned by Albert Einstein a century ago. In 2015, after years of exquisitely sensitive measurements, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by directly detecting these elusive waves for the first time. The source? The violent merger of two black holes over 1 billion light-years away. Since that landmark finding, LIGO and its international partners have detected numerous gravitational wave events, ushering in the era of multi-messenger astronomy. Our cosmic horizons continue to expand in other ways as well. Since the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995, the tally of known worlds beyond our solar system has swelled into the thousands. With an array of sophisticated telescopes and techniques at their disposal, astronomers are steadily uncovering a remarkable diversity of exoplanets, from super-Earths to hot Jupiters to the tantalizingly Earth-like worlds that may harbour the conditions for life. At the same time, scientists are grappling with the unseen components that shape our universe on the grandest scales. Dark matter, that invisible substance whose gravitational pull holds galaxies together, remains one of the most profound puzzles in modern cosmology. Equally perplexing is dark energy, the mysterious force thought to be accelerating the expansion of the universe against the inward pull of gravity. Together, dark matter and dark energy are estimated to comprise over 95% of the cosmos, with ordinary matter a mere afterthought. Unravelling the nature of these dark ingredients will be an essential step toward a more complete understanding of our universe. As we probe these mysteries, powerful new tools are coming online to extend our cosmic vision as never before. In 2021, the James Webb Space Telescope began its mission to collect infrared light from the farthest reaches of space and time. With its massive mirror and cutting-edge instruments, JWST will allow us to peer back to the dawn of galaxies, study the atmospheres of nearby exoplanets, and shed new light on the dark scaffolding of the universe. Gazing ahead, it's tantalizing to imagine what revolutionary discoveries await us in the coming decades and centuries. Will we decipher the nature of dark matter and dark energy? Will we detect signs of life on other worlds, perhaps even intelligent life? Will the long-sought theory of quantum gravity finally reconcile the subatomic world with the cosmos at large? As we ponder these grand questions, it's worth reflecting on the indomitable human spirit of discovery that has brought us to this point. Throughout our journey, we've met a cast of brilliant minds who dared to challenge the status quo and illuminate the mysteries of nature, often in the face of immense obstacles. From Galileo's defiant stand for the Copernican worldview to Marie Curie's trailblazing research on radioactivity, from Einstein's visionary insights on space, time and light, to Hubble's expansion of our cosmic stage, these scientific giants have collectively shaped our understanding of the universe and our place within it. Yet for every luminary in the spotlight, countless other scientists and unsung heroes have worked tirelessly behind the scenes to fill in the details, refine the theories, and lay the groundwork for the next leaps forward. Science, after all, is a deeply human endeavour, a global, multi-generational effort to construct an edifice of knowledge, brick by brick and insight by insight. It is a testament to what we can achieve when we allow our curiosity and wonder to guide us, when we follow the evidence wherever it leads. And so, my fellow traveller, as we conclude our journey through the annals of scientific discovery, I invite you to rest your head and let your imagination roam free. Dream of the wonders that await us in the vast and mysterious cosmos, and the marvels yet to be uncovered in the intricate dance of atoms and particles. Take comfort in the knowledge that no matter how dark the night may seem, the light of scientific inquiry will continue to illuminate our path to the stars. Perhaps you'll awaken with a newfound sense of awe for the natural world and a renewed appreciation for the power of the scientific method to reveal its secrets. If so, I encourage you to share that wonder with others, to support the noble pursuit of science in whatever way you can. For it is only through our collective striving, our shared commitment to the search for truth, that we'll continue to push back the frontiers of knowledge and build a better world for ourselves and generations to come. And if you've enjoyed our journey through the greatest hits of scientific discovery, I humbly suggest you like this video and subscribe to the channel for more soothing and edifying content designed to inform your mind and ease your slumber. Until next time, my friends, may your dreams be filled with the beauty and mystery of the cosmos, and may the spirit of curiosity guide you always. Good night.